Testing on YouTube. Testing on YouTube. Testing on YouTube. All right, I think it's working. It's working on YouTube. Now let's go to X. How's it going? 87GN 199. YouTube is good. All my mannerisms are being hyper-analyzed. All right. Let's see. X is on. X is live. Let's see. Is it working? Come on. Testing? Okay. It's live on X as well. How's it going, Jay? All right, let's get this stream started. Let's put the hood up too. You know, you gotta look the part. So how's it going, everybody? Okay, YouTube is complaining about the keyframe frequency. Jay loves autoencoders. Me too. Today we're going to be doing a little bit of a different stream. It's going to be kind of more of a marathon stream, I would kind of describe it as. But the title is called Generative 3D. And we're going to be looking at 9 different Generative 3D papers. So when I was trying to pick a paper for this week, there really wasn't a standout. There was a lot of different papers that did generative 3D stuff. And I was like, you know what? Let me try a new format for the stream, which is going to be reviewing all 9 of these. So no way we're going to actually get through all of them. So instead I figured, why don't we use this as an opportunity to test out where LLMs are right now for summarizing and gaining insight from these. So I have all 9 of the papers pulled up so we can reference them. So here's all 9 of the papers. Boom, boom, boom. And I also have these pulled up. So this is a site called Emergent Mind, which I've been using recently. It's a good, it kind of summarizes papers for you and ranks them according to how many videos there are and how many likes they get on X or different social media sites. But they also have these little summaries. So for every single one of these papers, I have pulled up the Emergent Mind, which is basically going to give us little GPT-4 summaries. These are made with GPT-4. And I also have a couple other little handy things here. So I have Gemini 1.5 Pro, which I think anybody can access now, but this is within the Google Playground. So this is kind of like the OpenAI Playground, but Google's version of it. And I just dragged all of the PDFs into here. So you can see here's 9 different PDFs for each of the 9 papers. You can see that roughly each paper is somewhere between 15,000 and 20,000 tokens, but that's still only 153,000 tokens out of the 1 million possible tokens that you can have in the context of Gemini 1.5 Pro. So this is pretty cool, right? It's basically the entire 9 pages or 9 papers. And then, yeah, I asked it, for example, there are 9 papers in total. Can you provide a summary for each of the 9 papers? And then there we go. I couldn't fit all 9 PDFs on ChatGPT 4 or Claude. So you can give one PDF at a time. But what I ended up doing is I ended up copying the abstract into a text file. So the abstract for each of the 9 papers, plus the link and the title and kind of a couple other things. And I gave that to GPT-4 and to Claude, and then asked Claude and GPT to summarize. So rather than kind of going through the exact paper, which is usually what I do in these streams, what we're going to be doing today is going through the summaries provided by a variety of different language models, basically the state-of-the-art language models, for each of these papers, and then compare the summaries and reference the paper and see if there's hallucinations in there, see which one kind of makes the most sense. And then once we're done summarizing all these things, I'm going to start asking kind of higher level questions, right? Because I'm really curious to see if we can use things like Gemini 1.5 Pro, which have such a long context, to provide insight, right? So one thing is summarizing and these needle in the haystack kind of tasks, but those don't really involve novel synthesis. You're kind of just mostly distilling, right? So it's basically just taking a bunch of paragraphs and reducing it to a couple sentences. But I want to see if it can kind of string things together. So I want to ask it, for example, which data sets it thinks are good, which techniques it thinks are good. Are triplane encoders a good idea? Score distillation losses versus some of the other kind of more novel losses that are in some of these papers. I want to see if it can do some actual kind of science and original thought synthesis. So that's what we're going to be doing today. It's going to be a long stream, so feel free to pop in and out as you will. I have a huge cup of yerba mate here, so let's get caffeinated. All right, we're going to start with the first paper here. So the first paper is called Diffusion 3D, Learning Scalable 3D Generative Models from a Video Diffusion Model. So a video diffusion model will be your Stable Video Diffusion or your Sora from OpenAI, right? This is a diffusion model which generates samples from some distribution. Traditionally, this has been an image distribution, but now we have video diffusion models, which rather than generating images from noise, they generate a full video from noise. The state-of-the-art for video diffusion models is definitely Sora, but Sora is not really available. So I think this one and the other one here, which is also going to be a video diffusion model, this is SV3D. Both of these are going to be using the video diffusion. I think this one, because it's Gen AI from Meta, I think it uses the EMU, which is the Meta's video diffusion model. But, all right. And again, all of these were released this week, so 18th of March, 2024. All right. This paper presents a novel paradigm for building scalable 3D generative models utilizing pre-trained video diffusion models, such as EMU. The primary obstacle in developing foundation, 3D generative models is the limited availability of 3D data. This is a theme that we're going to see time and time again in these papers. There really isn't any good 3D data sets. There's the popular ones are things like Objaverse, but even Objaverse has a bunch of has an object-centric bias. I guess Objaverse is literally the name object is in the name, but we're missing another 10x or 100x on that. And also using these 3D data sets is kind of a little gross, right? I think we want to eventually move to a point where we can use a generative model as a data set. And a lot of the original 3D work does this, right? They'll use something like Stable Diffusion to generate images, and then they use those images to train the generative 3D model. So people are basically taking the next step in that approach, and rather than using a image diffusion model, they're now starting to use video diffusion models. 3D data is not readily accessible. This results in significant disparity in scale compared to the vast quantities of other types of data. We propose using a video diffusion model trained with extensive volumes of text, images, videos as a knowledgeable source for 3D data. So this idea of using a 3D or a video diffusion model as the source of data, these data flywheels. Unlocking its multi-view generative capabilities through fine-tuning, we generate a large-scale synthetic multi-view data set. So you see this multi-view generative capabilities. What they're referring to there is that what you're going to ultimately need to create a generative 3D model is multiple views. So we'll see this here with this paper as well. But this Stability AI paper basically does the same thing too. They are fine-tuning a video diffusion model such that it generates these videos of basically hovering around an object, right? So it's like a multi-view, which means you're looking at the same object from multiple views, and they're fine-tuning these video diffusion models to generate these basically 360 shots of objects. And then once you have that 360 shot of an object, then it becomes easy to kind of reconstruct a 3D asset out of that. Okay, so they're going to have a fine-tuned video diffusion model for multi-view data. And once they generate that multi-view data, which they're going to call, do they have a name for this data set? I think they just call it 3M synthetic multi-view data. Okay, they probably have some name specific for it. Hopefully they release that data set. Can generate 3D asset from a single image and achieve superior performance when compared to the current state-of-the-art feed-forward 3D generative models, with users preferring our results 70% of the time. So most of these papers are going to claim state-of-the-art. You're going to see this in all the abstracts. They're pretty much all going to say they're state-of-the-art, but that's not really the case, right? Whenever they publish these papers, they only compare to the work that was available when they were working on this, which is like 6 months old by the time they released this paper. So even though all of them claim state-of-the-art, really, there can only be one state-of-the-art, right? All right, so that's the first paper. Let's read the summaries given to us by Gemini. Utilizes a pre-trained video diffusion model as a 3D data generator to overcome the scarcity of 3D data. I feel like that's a pretty good summary. Fine-tunes the video diffusion model with a rendered multi-view videos, okay, to unlock its 3D consistent generative capabilities. This allows for the creation of a large synthetic multi-view dataset used to train a feed-forward 3D generative model. Okay, I feel all of that seems pretty fine. The rendered multi-view videos, rendered implies rendered via a game engine to me. I would have preferred the word generated, but generates high quality and 3D consistent assets from a single image in seconds, outperforming existing feed-forward generative models. Is that correctly what they said here? Superior performance in seconds. So you see how it kind of copied this exact phrasing here. Single image in seconds. Single image in seconds, outperforming existing 3D generative models. Okay. I would say that's a pretty good summary. Diffusion. Diffusion 3D introduces a... That's not the right one. Is this it, the right one? Diffusion 3D. Yeah, okay. Introduces a scalable 3D generative model using video diffusion models. Due to the scarcity of 3D data, okay, fine-tuning a video diffusion model with a large synthetic data set. Diffusion 3D can generate 3D assets from images rapidly and outperform existing models. So this is not quite right. Diffusion 3D is fine-tuning a video diffusion model on a data set of rendered 3D objects in order to generate a large synthetic data set of multi-view videos. So this is a little bit... You got a little bit confused there about the synthetic data set is the output of this fine-tuned. Yeah, through fine-tuning, we generate a large synthetic multi-view data set. So ChatGPT got a little bit confused there. Let's see Claude. Diffusion 3D. This paper proposes a pre-trained video diffusion model as a knowledge source to generate large-scale synthetic multi-view data sets. That's 100% correct. I think that's a good way of phrasing it. For training feed-forward 3D generative models, the resulting model can generate a 3D asset from a single image in seconds. There you go. That same phrasing. GPT doesn't catch on to that phrasing, but it's interesting to see that both Claude and Gemini 1.5 really remember this one specific phrase there. A single image in seconds. And outperforms current state-of-the-art models. Okay. So Claude drops the state-of-the-art. Okay. Let's confirm that. So if we actually go here we have another overview. This one's also going to be generated by GPT-4, but this one has more context. So as I said before, this website, it consumes, I don't exactly know what it does, but it consumes the whole text, right? Versus here, I only gave it chunks of the text and the abstracts. So these don't really have the full information, but this one does. So in this summary, generate large-scale synthetic multi-view datasets using a pre-trained video diffusion model, training the 3D models that outperform current state-of-the-art, It's not in speed, so that's incorrect. Describes the process of fine-tuning EMU video model with rendered multi-view videos. Okay, so now we know that they are using the EMU model, which is Facebook's video diffusion model, generating 2.7 million high-quality, consistent videos. Scalability and performance presents a significant advancement, suggesting a promising future. Okay, I think that's a fine summary. Let's actually go to the figure here. This is figure 2 in the vFusion 3D. I think this is a nice little summary. So you start with the video diffusion model, right, which is pre-trained. They're going to be using EMU. You could use stable video diffusion. You could use Sora. You're going to fine-tune that on 3D data. So you're going to have some actual 3D data sets such as ComboVerse, and you're going to basically just render images along a camera trajectory, probably just a little ring over the top. And then you're going to make a video out of that. You're going to fine-tune your video diffusion model on that video data set. That will create effectively this multi-view data generator, which just generates videos given whatever input you have here, either text or images. And now you see this is the video that's generated. You can cut that video into individual frames. And then here, that's being used to supervise this. So what is this? This is have a single image. That image is being fed into whatever this is. This is, what is this? Generates 3D representation and renders novel views. So this is a triplane encoder here. So this is you could think of it almost like a position embeddings for 3D representations. It glues representations onto these 3 axis-aligned planes or orthogonal planes, and that allows you to query any point within this voxel and get a specific feature vector corresponding to that. Once you do that, you can render it. This is probably a nerf, if I had to guess. This looks like a nerf. Let's confirm that. Feed forward. What exactly are they using? Vested into a nerf. Okay, I see the word nerf. EMU video, blah, blah, blah. LRM, EMU video. Large reconstruction model is a feed-forward model. It utilizes a pre-trained vision transformer dyno. That makes sense, given this is a Facebook paper. Also sent to the image-to-triplane. Okay, here you go. Used by an image-to-triplane decoder via cross-attention. Okay, so they're basically using dyno features with this triplane encoder to get a nice little representation. And then that little representation gets fed, blah, 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 into a multi-layer perceptron. There you go. So this is a nerf. Okay. And then once you have that nerf, then you can render from multiple different views to match whatever the views you have up here, and then just use some kind of reconstruction loss and push the gradients all the way back into your, probably not into the dyno. I bet you they freeze the dyno. Training is conducted, supervised with multi-view. Here's your reconstruction losses. So they have LPIPs. This is mean squared error, and then the learned perceptual simulate, something like that. Okay. Pretty basic. Good morning from Australia. How's it going? Economic sanity? Okdon, question from Okdon. I'm guessing those chatbots are just summarizing the abstract, which is already a summary in itself. Yeah, these are for sure. But even this one, so Claude was also given the abstracts, and I feel like this is a nicer summary than GPT, which had the same abstracts. But, okay. So that's the first paper. We've made it. It took us about 20 minutes. I think we can hopefully do this second one a little bit faster. So the second one is a very similar paper. This is from Stability AI, and maybe a little tangent here. Stability AI is currently imploding. The CEO left, and also I think this guy left, Robin Rombach. A bunch of the kind of senior people left. It doesn't look very good, but we kind of saw this coming. Stability AI was kind of just using a bunch of venture capital money to subsidize open source efforts, right? They published all their work, they published all, open sourced all their models, which is great for the open source community and great for the kind of moving AI forward and democratizing AI, but there really isn't a business model there, right? They never really had a business model, and if you don't have a business model, people aren't going to give you money, because the venture capitalists, they're not doing it for the love of technology, they're doing it for the love of money, right? They need to return money, so it kind of makes sense that eventually they would run out of money, and then as soon as they run out of money, the company kind of implodes, which is very unfortunate, you know, kind of sucks, because I loved reading their papers and I loved that they open sourced all their stuff, but, you know, good things don't last forever, so I guess we'll we'll read this paper as a form of a eulogy or something. But 18th of March, novel multi-view synthesis, this same idea of generating multiple views of a thing, 3D generation from a single image. So they're feeding a single image into this SV3D. You get this multi-view, and then you feed it into probably a NeRF. Let's see. A latent video diffusion model for high resolution image to multi-view generation of orbital videos around a 3D object. These methods have several limitations. Either limited views or inconsistent novel view synthesis. This is the Janus effect that you sometimes see, where certain views, such as the frontal view, are easy to generate, but other views, such as the back of an object, are very difficult to generate. There's a bias in these generative image diffusion models. So novel view synthesis has been difficult when using these image diffusion models, but now that it seems like people are using these video diffusion models, maybe we get rid of some of that Janus problem. Adapts image to video diffusion models for novel multi-view synthesis. We propose improved 3D optimization technique, extensive experimental results, and this one is also state-of-the-art, but as I said before, they're all going to say they're state-of-the-art, but really only one of them can be. And hopefully by the end of this marathon, we can figure out which one is the actual state-of-the-art. All right, let's read the summary for SV3D here. Adopts a high-resolution image-conditioned video diffusion model for novel view synthesis. Seems fine. Leverages the temporal consistency inherent in video diffusion models to achieve spatial 3D consistency in the generated images. Seems fine. It's just like wording it in a weird way. Like, you know, the sentence is correct, like technically correct, but it's like, it's just kind of like weirdly worded. Here, right, they're mentioning the temporal consistency, right? Talking about how video diffusion models, they will keep the same object over various frames much cleaner than if you're doing some kind of image diffusion model and you're just generating 3 views from the front view, the back view, and the side view, right? There's nothing that's necessarily forcing each of those 3 separate renders to be the same consistent object, versus in a video diffusion model, because you're rendering all of the frames usually at the same time, you're kind of rendering in the spatial and temporal dimensions, you're keeping more consistency. There's kind of regularizations that prevent the object from changing too much from the first frame to the last frame. Produces high-quality meshes from single images, demonstrating superior performance and 3D reconstruction. Okay. Let's see what GPT-4 summarizes. Latent video diffusion model enables high-resolution generation and orbital videos around 3D objects from a single image, offering multi-view consistency and explicit camera control for novel view synthesis, improving upon previous 3D generation methods. Seems kind of lame, to be honest. I don't know. It doesn't really give me the important parts. Image to video diffusion model, multi-view consistency of video models while adding explicit camera control. This is weird. I would more... See, they chose multi-view consistency here. They chose temporal consistency, right? In a video diffusion model, the different frames are representing different points in time, versus here, it's saying that it's kind of like assuming that your video is representing multiple views of the same object, but like technically multi-view video isn't necessarily correct there. While adding explicit camera control, the proposed 3D optimization techniques using SV3D and its outputs demonstrate state-of-the-art on both novel view synthesis and 3D reconstruction. Okay. Let's read the longer GPT-4 summary here. Generating multi-view images from a single image using latent video diffusion adopts the stable video diffusion framework to include camera poses and clip embeddings, achieves state-of-the-art performance, and introduction of a soft masked score distillation sampling. This is a very common loss that we see in these type of papers. Represent a novel contribution to improving 3D reconstructions. Okay. Now let's look at the actual figures. So that's the summaries. Let's look at the actual figure, see if we get a better idea here. How's it go? Everybody seems to have opinions on the imminent death of Stability AI. Switzerland, you have no access to 1.5 Pro. Huh. I wonder if you can use a VPN or whether they know based on your Google account where you are. I don't know. That kind of sucks. It's pretty good. I actually fed it my journals. So I write my journals every day before I go to sleep. And I have maybe just a little chunk of text. And I fed it like years worth of journals into Gemini 1.5. And I was asking it questions. And it's actually pretty good. It was able to do a bunch of needle in the haystack kind of tasks. And I was asking it kind of like high level things, like give me some advice, like what do you think I should do? Like what are some flaws that I have? What are my strengths? And it was actually pretty good. It's pretty trippy. We're very quickly approaching an era where these language models are going to have more context than you can even have, right? Because as a human, there's a limited context, my memory isn't that great. I can really only remember a couple months back with precise detail. And then once you go longer than a year, it's like you start to forget a lot of the detail, but the LLMs know that detail, right? So they can kind of pick up on patterns that you as a human will not be able to pick up on. So it's going to be a crazy world. Will there be a paper review on cognitive AI like causality and reasonings? Is that a specific paper? That just seems like a high-level concept, economic sanity. Okay. Let's go back to this. SV3D architecture. We add the sinusoidal embeddings of the camera orbit elevation and azimuth angles. So these two here. So this is the camera position. So the elevation is basically going to be how high it is, like this. And then the azimuth angle is kind of like the rotation, I guess. They're feeding this explicit camera information, combining it with what is T, noise step T. So, right, this is a diffusion model. So the diffusion is happening over a series of time steps. Fully connected, embedding. Okay, so those are used to condition the conv blocks here. This is the UNet. The UNet is operating in this latent space. So here your Z of T is your latent space. You see that it's coming out of this image encoder. So you have an image encoder that's, here they call it the VAE, variational autoencoder, produces this latent representation. That latent representation is what is being used to denoise. With this UNet, the UNet is conditioned on both the camera information and the time step. And then also you see they have spatial attention and temporal attention because this is a UNet, this is a video diffusion model, right? If this was just an image diffusion model, you wouldn't have this temporal attention. You would just have spatial. They're using just the clip. This seems a little, because once you're feeding each of the frames of your video into this clip, you're kind of losing a bunch of information, right? You're kind of you're trusting that the clip embedding is encompassing all the important parts of this frame. But we know that clip as an embedding model only really represents kind of the semantic and high-level information in a frame versus some of these other encoders, such as this one here that they use. And this one, they use the Dino encoder because this is a Llama or a Meta paper. But the dyno encoder is a lot better at kind of the details and the edges, and because it's used for dense prediction tasks like segmentation. So I feel like for something where you want the edges to be very good because you're doing this kind of multi-view video, they should have probably done an ensemble of representations here, including a dyno representation, perhaps even the representation that comes out of a SAM encoder. But, okay. Maybe that's what this is for. So that's why they only bother to do... Okay. Use two types of orbits. Static orbit versus dynamic orbit. So dynamic orbit seems to zoom in and out and kind of be much more varied in terms of the angle, versus the static orbit, they're all at the same height. They're all equidistant from the center of mass of this object. Okay. So, and then what eventually do they do with this video? Do they feed it into a nerf? Okay, there you go. So once you fine-tune this video diffusion model, then you end up with a video diffusion model that's now been fine-tuned for multi-view videos. Now you have this fine-tuned video diffusion model that generates these like basically 360 fly arounds of objects. And once you have that, then, okay, it seems like basically they're doing exactly what they do in this paper. Here they have a triplane nerf that's conditioned on an image. And here they have basically the same thing, image plus geometry used to create this nerf. Here's the nerf stage. DMTET. This is how you get a texture out of, or not a texture, a mesh plus a texture out of the nerf, right? The nerf is an implicit representation, and you need to turn it into an explicit representation, such as a texture and a mesh. So they do that with the marching cubes and the DMTET. Here's the actual loss, the same SDS loss, but they have a variant of this, soft masked. So they probably segment out the background and then prevent, or only use the foreground for this SDS loss. That's probably what it is. Reference plus random orbits. Visibility mask. I bet you that's a SAM, segment anything model. Okay, and then the gradients basically go all the way back through this mask loss into here, through these renderers, right? The nerf rendering is differentiable, so you can go backwards through it, and once you go backwards through it, then you can push gradients into that. So this is very, very similar to this paper. It's almost identical. It's basically just fine-tuning a video diffusion model to make it a multi-view video diffusion model. Once you have that multi-view video diffusion model, you use it to generate data for a nerf, and that nerf is basically trained with these reconstruction type losses. All right, so both meta and stability releasing kind of identical papers there. Which one do we think is better in terms of quality? Let's see. Usually at the end of these, they have nice little... Let's compare these. All right. Hat looks pretty good. Motorcycle looks pretty good. These are the failure cases. Damn, okay. V-Fusion 3D. Looks okay. There's still some mistakes there on this bear. Let's see what we got here. You can see the topology on these looks terrible. So here they're comparing to a bunch of other 3D generative models, but these are producing absolute shit. So it's easy to get state of the art when you're comparing to these. The topography on this looks very nice. There is also, you see it doesn't have this Janus problem. See how the front of the bear is very clearly the front of the bear and the back of the bear is very clearly the back of the bear. This object is easy just because it has this bilateral symmetry. I wish they would have shown us the back of this. I would have loved to see what's on the back of this backpack. But the fact that it has a backpack is pretty good because you only get the very subtle hint of a backpack there. Pretty good. All right. How often do I stream? Question from PSO Glab. I stream twice a week on Saturdays and Sundays. Usually I stream later than now, and usually I do like a one paper, you know, so I can really deep dive, but I'm trying something new today. This is a little bit more raw than my usual streams. Usually I feel like I come in with like, and I really fill in the time, but this feels more raw, and I apologize if you feel like you're wasting your time by watching this. Okay. How's it going, Majetti, by the way? Let's look at this third paper. GaussianFlow. Splatting Gaussian dynamics for 4D content creation. This is a Gaussian splat paper. So these first two papers that we've read up until now, neither of these uses Gaussian splats, right? These are video diffusion models that are fine-tuned, and then ultimately the representations that they use for 3D are a NeRF, so that they can actually push gradients into it, and then both of them turn it into a mesh. So both of these papers, neither of these is using Gaussian splats, and now we have our first Gaussian splat paper coming out of Google, University of Southern California, Penn State, Max Planck Institute. Creating 4D fields of Gaussian splatting. You're usually used to 3D Gaussian splatting. 4D there means they've added the time dimension, so it basically means a 3D Gaussian splat that is varying over time. So much like a video is a sequence of frames, you can kind of think of a 4D Gaussian splat as a sequence of 3D Gaussian splats. While the optimization can draw photometric reference from the input videos, directly supervising Gaussian motions remains unexplored. We introduced, I don't know about that. We've definitely read a bunch of 4D Gaussian splat papers. We introduced a novel concept, GaussianFlow, which connects the dynamics of 3D Gaussian and pixel velocities between consecutive frames. GaussianFlow can be efficiently obtained by splatting Gaussian dynamics into the image space. This differentiable process enables dynamic supervision from optical flow. Okay, so they're going to be supervising from optical flow. These are actually Sora videos, right? This little otter on the board, this is definitely coming from Sora. Especially for content with rich motions that are hard to be handled. Color drifting happens in 4D, can be improved. Superior visual quality on extensive experiments demonstrates our method's effectiveness. Quantitative and qualitative. So I'm a little confused about what exactly is going on here. Image to video. Okay, you have a bunch of frames. Then what are you doing with these frames? Photometric mean squared error. 0, 1, 2, 3. 3D Gaussian initialization. 0, 1, 2, 3 is actually one of the 3D models that they compare to here. Stable 0, 1, 2, 3. So here you go. So they're actually only using that to get the starting point. So one of the problems with these 3D Gaussians is that you have to initialize them, right? So you can think of like a 3D Gaussian is just a set of little Gaussians, but each little Gaussian has some XYZ position, and you don't have those XYZ positions beforehand. So you have to initialize this set of 3D Gaussians and choose a little XYZ position for each of those little Gaussians. So here they're using this SDS from a pre-trained 0, 1, 2, 3 in order to create the initial starting position of all these little Gaussian points. Once you do that, then you could probably just frame by frame, this is probably what they mean by photometric here, and use the same 0, 1, 2, 3 SDS, where your SDS is pushing gradients into the Gaussians directly, and then you run this a bunch of times, eventually get something that looks a little bit more reasonable. 4D Gaussian field optimization. GaussianFlow. Okay, I think I know what this is. So optical flow is basically when you have multiple frames in a video, the optical flow is trying to tell you what in that video is moving, but it's doing it kind of from the pixel level. So you can see here, in this little video of a dancing frog, right, the background is static, which is why the optical flow is completely white for the background because nothing is moving, versus you see the little frog itself, maybe this arm moves up, this arm moves down, but optical flow is like, it's not very intelligent, right? It's not, optical flow doesn't usually have like a semantic understanding about what's going on. It's more just looking at it as like a blob of pixels, and it says, oh, this like blob of pixels kind of seemingly moved down a little bit from this frame to this frame, therefore I'm going to just give you motion downwards for this general blob area. So optical flow is not like super intelligent in that way. But what they're doing is, it seems like they're running optical flow for every probably consecutive pair of frames here, and then they distill what they're calling Gaussian flow here, which is probably just the same concept, except rather than doing it in pixel space, you're now doing it in the Gaussian splat space. It's kind of cool. And then once you do that, I suppose you can, right, because it's a Gaussian splat, you can render it from any view. And here they're rendering this 4D Gaussian splat from a multi-view. It looks like a multi-view, but this is different than this, right? These are meshes. So these are meshes that come out of a marching cubes that's done on a nerf. So this is a nerf turned into a mesh. This is just a render of a Gaussian splat directly, which is why it has that kind of like fuzzy look to it. But looks pretty good. Okay. Is optical flow kind of like a vector field? Yeah, very similar to that. That's a good intuition to have for optical flow. Question from Unsupervised Universe. You can probably apply SD on top of the SV3D and then make that the dataset for the nerf. Not sure if that was covered on the other paper just got here. Yeah, SV3D is Stable Diffusion. They are using this UNet here is not trained from scratch. This is the pre-trained video diffusion model from Stability AI, and what they're doing is they're fine-tuning it on these multi-view videos of objects which come from some 3D object dataset, and then you end up with a video diffusion model that generates these kind of like multi-view videos like this. What they're calling reference orbits. So this is pre-trained video diffusion model to a fine-tuned video diffusion model, and then use that fine-tuned video diffusion model as a way to generate data sets for a nerf. And then once you have that nerf, then you generate the meshes with this marching cubes and DMTET. And then that's what they're actually comparing here. Right, versus here, this is using a video diffusion model and then using the optical flow between the frames of the video diffusion model to create what they're calling Gaussian flow. And then the Gaussian flow, you could literally wrap this entire, you could probably frame by frame, like run an optimization loop that just basically infinitely churns right here, right? Where it's trying to match the Gaussian flow to the optical flow, and it's also trying to make sure that every single frame, if you pause it and you have your little Gaussian splats and you render an image, that image should match with score distillation sampling what's coming out of this 0, 1, 2, 3. So here they're using this pre-trained 0, 1, 2, 3 and the optical flow combined with the pre-trained video diffusion model in order to generate these 4D Gaussians, which I actually think is like much more representative of what we'll see in the future. I think that in the future we're I know some people get annoyed whenever I mention this because some people think that textures and meshes are the future, but I think textures and meshes are a legacy format at this point. So when you're sitting there in your VR headset in 2028 and you're talking to your VR headset and it's rendering things for you, it's not going to be rendering meshes and textures. It's going to be rendering this. It's going to be rendering four-dimensional Gaussians that you're... So like this kind of like misty kind of like effect, it'll probably be more misty than low poly, if you want to think of it that way. Here's optical flow, what it looks like. So you see how optical flow is defined with respect to you need two different frames there. So the flow, optical flow between frame T1 and T2, and you can see how This is kind of weird, actually. The whole background is white, but for some reason it has non-zero optical flow. Optical flow values of the background should be ignored because dense optical flow algorithms calculate correspondences amongst background pixels. We calculate optical flow on rendered sequences, comparing blah, 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 due to the ambiguity. Okay, so I guess that's probably what they removed. They got rid of that. All right, we actually didn't look at the summaries for this. Let's see. GaussianFlow. Key idea. Introduces the idea of GaussianFlow to bridge the dynamics of 3D Gaussians, which is dynamic 3D Gaussians is just another way of saying 4D Gaussians, and pixel velocities between consecutive frames. There's your velocity or vector field, right? Pixel velocities between consecutive frames is another way of saying optical flow. Enables direct supervision of 3D Gaussian dynamics by matching Gaussian flow with optical flow on input video frames. This improves the accuracy and realism of generated 3D content. Significantly improves 4D dynamic content generation, particularly for content with rich motions. Also resolves the common color drifting issue. Okay. Let's see what GPT tells us. Gaussian Flow introduces a method to create 4D content. 4D content? That seems too generic. By connecting 3D Gaussian dynamics with pixel velocities. That also seems a little weirdly worded. Enabling high-quality dynamic content generation and novel view synthesis through efficient Gaussian splatting, overcoming common challenges like color drifting. I don't like the summary at all. It's not incorrect, but like 4D content? Pixel velocities? Like, I don't know. Let's see. Claude. A paper introduces Gaussian Flow, which connects the dynamics of 3D Gaussians and pixel velocities between consecutive frames. I like that a little bit more. Enabling direct dynamic supervision from optical flow. Dynamic supervision? That doesn't necessarily mean anything. The method significantly benefits 4D dynamic content generation. That's better. And novel view synthesis with Gaussian splatting, resolving common color drifting issues and achieving state-of-the-art results. There really isn't novel view synthesis in this. This is not about novel view synthesis. This is more about training a 4D Gaussian from a video. Okay. I would say all those summaries were kind of mid. Let's look at the summary here. So this is the summary from Emergent Mind. Introduces Gaussian Flow to connect 3D Gaussian dynamics with 2D pixel velocities, enhancing 4D content creation. Proposes a method to directly supervise 3D dynamics using optical flow data, improving handling of motion-rich scenes. They all mention this color drifting, but that doesn't seem like a huge issue. That's just like some random fault of like current time 3D Gaussians, but I feel like once we scale 10x, it'll just disappear. Efficient and differentiable computation of Gaussian flow, facilitating advancements in 4D content generation, novel view synthesis, highlights potential for real-time rendering applications and future research directions for smoother dynamics and temporal consistency. Okay, a little bit more fleshed out, but this is probably the better figure for understanding this. Let's see. Between two consecutive frames, so here's consecutive frame t equals 1 and then t equals t2, so these are 2 frames, so you see there's 2 little Gaussian splats here, and the Gaussian splats have moved. Okay. A pixel x t1, so here they're saying, okay, here's the Gaussian splats, and you're splatting them into 2 dimensions, right? You're splatting them from this 3-dimensional voxel in which they live into this 2-dimensional pixel space using a camera. So here you have a camera, right? And the color at this particular pixel in pixel space is going to come from the overlap of those Gaussians, right? These Gaussians have a specific opacity, and then you're sorting them with respect to the camera position so that they're kind of like overlapping on top of each other. And that's what you're getting there. Will be pushed towards xt1 to xt2 by the 2D Gaussian eye's motion IT1 to IT2. So IT1 to IT2, and then JT1 to JT2, where I and J are the 2 Gaussians. We can track XT1 and Gaussian I by normalizing it to canonical Gaussian spaces X, hat eye and unnormalize it into image space to obtain XIT2. Okay, so here's the transformation that they're talking about. They're going from image space, so in this 2D pixel image space, you have this Gaussian, which is JT1. It has some center, right? Mu JT1. So each Gaussian has an XYZ position. Here's the center of it, mu. Then canonical Gaussian space, and then image space. So they're going from image space to image space through this canonical Gaussian space, which is like an abstract space. Okay. Yeah, we've seen this before. I think this reminds me of tracking everything everywhere all at once. I think it was the name of the paper, but it was like this paper where they were trying to do something similar to the optical flow. But the way that they were doing it is they had this like canonical, almost like a 2.5D space, and they were trying to project everything into that canonical 2.5D space and then use that to basically condition going back into the real pixel space or 3D space. So they're kind of doing something similar here. This shift from Gaussian eye, the Gaussian flow is defined as the weighted sum of shift contributions from all Gaussians covering the pixel. Okay. So in optical flow, right, so the output of an optical flow is this. So you see this yellow square represents this pixel, and optical flow will give you the flow for every single pixel in pixel space. So you see how the optical flow, what it's telling you is, okay, this pixel here moved over here. So it moved 3 frames over, or 3 pixel spaces over. And they're basically combining the optical flow, which is this yellow line, with the what they're calling the Gaussian flow, which is the movement of these Gaussians, which is these black lines. And what they're doing is a weighted sum of both of these. So all the different Gaussian splats that were overlapping in that specific particular pixel and image space, you combine using a weighted sum the shift of all of those, and then compare that to the optical flow, and that's how you're getting the gradient that goes back, because you're trying to make those consistent. Kind of cool, you know, but I feel like maybe, like, what is the weakest link in the chain here? Like, I feel like the weakest link in the chain is honestly the optical flow. Right? Because envision, like, for example, an object such as like something that's very like this, right? Like that's all black, and you're just rotating it like this, right? Like that. That is going to be a nightmare for optical flow because it's all just the same exact color, which means it's very difficult to determine like what exactly the fuck is going on, because you're just, optical flow is based on pixel space. So we need to get rid of that somehow. Okay. Where are we at? 8:52, and we're 3 papers deep. I think we're making good progress. So we're 3 papers in roughly an hour, and we got another 6 to go. Okay, let's go to the next one. What is going to happen to traditional animation? Any advice for students that are currently focusing on Blender and more traditional animation techniques? Well, traditional animation is going to disappear. That's the hard truth, is that making an armature, right, the skeleton and animating it, that's going to eventually disappear, but the desire for that will continue, right? Like ultimately, animators have a job, and people who know Blender, they have a job because people want content, right? People want to see video, movies, and like CGI and awesome stuff. So that desire is always going to be there. So if the tools that you need to use to create the content change, that doesn't mean you're going to lose your job if you know the previous tools, because here's the thing, nobody knows the new tools, right? So it's not like you have to catch up to someone who's been using modern tools with these new generative 3D tools, it's not like you have to catch up to them. They haven't been using it for that long, right? Everybody's starting from the same place. And if anything, if you already are familiar with all the previous kind of animation tools, you're going to pick up the new tools much faster. So that's usually how all technical fields work, where your skill set gets outdated constantly. Like basically every 2 to 3 years, the skill set that you have is going to be outdated and you're going to have to learn a new skill set. But the secret is that every new skill set is not very far away in skill set space from the previous skill set. So if you're good at this current generation of tools and the next generation of tools comes out, you're going to be learning much faster and getting good at it much faster than anybody who's just starting for the first time. So if you're really good at Blender right now, you're not going to be using any of the things that you're doing in 2 to 3 years, but if you just learn all this new stuff, you're going to be way ahead of everybody, because they're going to them learning this new stuff is going to be harder for them because they don't have the abstractions and kind of the high-level concepts that you have built up over your career. So you got to keep running, I guess, is the only advice, is that don't stop running. If the only thing you can do is you stop running and then you fall behind. But as long as you keep chugging along and you just wake up every day and you just keep doing your thing and you keep learning, and the new tool comes out and you just keep learning and keep learning, you're going to be good, because that desire will always be there. The demand will always be there, which means that there will always be a need for people who can create interesting and compelling 3D content. Okay. Combining Gaussian splatting with diffusion, add noise to all the Gaussians and then learn this reverse. Can this be done if compute is available? Yes, you could definitely do that. The problem I see with that, Aditya, is that there isn't a huge data set to learn a diffusion model in pure Gaussian splat space. So if you think about the successful diffusion models, such as image diffusion models and video diffusion models, the reason those are successful is because there's a huge amount of images on the internet, and there's a huge amount of videos on the internet, right? So it's very easy to go from noise to image because you have millions, or like probably billions of images. But that's not the case with Gaussians, right? You don't have billions of Gaussian splats. But what we're learning is that we're going to be able to create Gaussian splats from videos, right? So these guys are basically saying, hey, here's a technique to feed a video and get a Gaussian splat, a 4D Gaussian splat from it. So once we do that, then we can take every single YouTube video, feed it into this, get 1 billion Gaussian splats, and then once you have 1 billion Gaussian splats, then you can train a diffusion model that goes from noise straight to Gaussian splats. And that's probably going to be what's in your VR headset in 2030, right? You're going to have a text condition or a speech conditioned 4-dimensional Gaussian splat diffusion model. Assuming the skill set required for new tools is obtainable for people working in 3D art. Early on, they might be more technical for beginners. Yeah, there is more so on the skill set. And I apologize if people are getting annoyed that I'm not reading the papers. Like, I figured it's a 4-hour stream, so I'll spend a bunch of time on tangents and answering questions. But there are people that are salty, because one of the reasons that, for example, people are salty in programming is that it's easier to learn how to program when LLMs were around than when they weren't around, right? So a lot of people who spent many years learning how to program before LLMs, they're kind of salty that people can just now get much better at programming much faster because they have LLMs to interact with, right? But you have to realize that I benefited from that as well, right? So whenever I learned to program back in the day, I had Google. So I could go and search for things and find it, right? Imagine how much easier that was compared to someone in the 90s or the 80s who had to learn from like a literal fucking book. You know, like I saw at one point there was people who were learning how to program from like an actual physical fucking book printed on paper, right? And they were probably pissed at my generation when we could go on the internet and we could go on Stack Overflow and just like learn from the internet, which is a much more efficient way of learning. So I think that's going to happen with every single skill set, where learning how to do 3D like 10 years ago, it's going to be way harder than learning how to use Stable Diffusion, right? Learning how to like paint with a paintbrush like Leonardo da Vinci style, that's orders of magnitude more complicated than learning how to use Stable Diffusion, where all you have to do is just sit there and type a prompt and it just appears, right? So the tools are getting easier and easier and easier, but that doesn't necessarily mean that the mastery of those tools is getting easier and easier and easier, right? Even though Stable Diffusion and these image generation models are very easy to use, the difference between someone who's a professional artist who knows how to use Stable Diffusion very well and someone who's just like some noob who's just like putting in random text in there, there's still a big difference between that. So I don't know. I think that it's a good thing that everything is becoming easier. It's becoming easier to learn how to program. It's becoming easier to become a 3D artist. It's becoming easier to learn anything because these language models are very, very good teachers, right? And the workflow itself becomes easier and easier, but don't see that as a negative thing, right? You don't want to be some gatekeeping, salty motherfucker. Like, you should be happy that more people can use these tools, right? Be happy that these things are democratizing and they're becoming easier over time rather than harder over time, right? You got to frame it as a positive thing. So, I don't know, don't live in the cage of negativity where you spent all this time learning it and now it's useless because now everybody can do it. You know, see it as a positive that everybody can do it. I don't know. I'm in a very zen, positive mood today. All right. Generic 3D diffusion adapter using controlled multi-view editing from Stanford, San Diego, UC San Diego, Stanford. Okay. 19th of March. Let's see. This one looks a little bit more complicated. We have a 3D input. So this is some kind of mesh, right? You can see it's got vertices, it's got faces, edges, and then MV edit. Multi-view editing. So we see, again, this idea of multiple views. Okay, here's the 0, 1, 2, 3 again. So there's that same pre-trained model, right? The same one that they were using here, the 0, 1, 2, 3. Here they're using it basically to push gradients into this Gaussian splat so that the semantic content or the actual kind of like appearance of this object is similar to what comes out of here, right, with this score distillation sampling. Here, they're using it to generate the multi-view. So you have an input image and you get multiple views. Here you have 12 different views of this horse or astronaut riding a horse, which is an inside joke to some of the earliest images that were generated. And then what are they going to do? Text-guided 3D to 3D. Instruct 3D to 3D. Oh, okay. I think I know what this is. This is basically instruct pix to pix, but in 3D. Let's see. Open object synthesis has been lagging behind image synthesis. To ball this, recent works have investigated multi-view diffusion. This paper proposes MV edit. Functions as a 3D counterpart of SD edit, employing ancestral sampling. Ancestral sampling? The fuck is that? Ancestral sampling process. Blah, 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 blah. Is ancestral sampling just a fancy way of saying you're distilling from a pre-trained? Or is ancestral referring to the earlier time steps? Is that what it means in a diffusion process? To jointly denoise multi-view images and output high-quality textured meshes. Jointly denoising. So you're denoising in all the images simultaneously, which means that there's some kind of representation that you're kind of making sure all of them are constantly pointing to that same thing. Right? So you wouldn't want to denoise them individually because then they would kind of move in different directions. You would end up with slightly different horses and astronauts. So you want those to be consistent, which is why you're going to jointly denoise them. MV Edit achieves 3D consistency through a training-free 3D adapter, which lifts the 2D views into a coherent 3D representation, then conditions the 2D views of the next time step using rendered views, with an inference time of only 2 to 5 minutes 2 to 5 minute inference time is not an only 2 to 5 minutes. That's a lot. Achieves a better trade-off than score distillation. Okay. So what they're calling this joint denoising using ancestral sampling, basically it's probably going to be a slight improvement over score distillation, but I bet you it's just slightly more complicated, slightly more overfit, a little bit more inductive biases than the distillation SDS, which is what they're using for these other ones here, this SDS. Particular evaluations demonstrate state-of-the-art. Yet again, 4 for 4 papers claiming state-of-the-art. We introduce a method for fine-tuning 2D latent diffusion models on small 3D datasets, enabling fast, low-resolution text to 3D initialization. Okay. This paper looks a little complicated. It seems like they tried to just put too many different things in one paper. Comparison among 3D-aware multi-view denoising architectures. So if you have a noisy multi-view, which is multiple images of the same object, 2D net, denoised multi-view. Okay, so basically, what are you conditioning this 2D net on? Probably conditioning it on some kind of text or something. You're starting from noise, going to image space. Here you're starting from noise, also going to image space, but this is the 3D nerve, so 3D aware denoising. This is basically what they're doing here, right? Where ultimately you're trying to push gradients into this nerve here. So this is 3D aware denoising. Blur-free 3D aware denoising with skip connection. Dude, what? So they go from multi-view 2-dimensional images, create a nerf out of that, and then create multi-view 2-dimensional images again based on the nerf. But then this part here also receives information from the original 2D multi-view. And they're calling this blur-free 3D aware denoising network with skip connection. Simplified 3D adapter reusing the... So this is almost like an autoencoder, but the bottleneck of the autoencoder is a nerf, which is kind of crazy, right? Autoencoders start in image space, and then they go into this compressed bottleneck, which is a little vector, which represents the image space. And then you have the decoder part, which takes that little vector and then blows it back up into image space. Here, they're doing something similar in concept, right? It's not actually similar, like, technically, but what they're doing is they're starting from multi-view images, then they're compressing that down into a 3D nerf, and then you're taking that 3D nerf and blowing it back up into multi-view images. That's fucking weird. Simplified 3D adapter reusing the last denoised RGB. What? Last denoised multi-view. Okay, so here you're going to have many images, many multi-view images. Here you just have one, so you're taking the last one of those. You're putting that back through the nerf. What does this even mean? And then conditioning this thing again? Dude, what are they doing? Oh, okay, because here's the thing, is that some of these are the edits that you want. Okay, that makes more sense. This isn't a pure reconstruction paper. This is an edit paper, because it's not... They're not just trying to create the 3D thing, or else they wouldn't need to do this. The problem is they have different sets of images, right? They have the image that you have representing the actual object, and then they have the image of the thing that you want to get to, which is, for example, this zebra, right? So part of this pipeline is about just getting a good representation, or in this case, it's a nerf, 3D representation for the actual object, but then you also want to move it towards some other image semantic kind of thing, right? So rather than being a rocking horse, you want to move it in zebra space, right? So kind of similar to what they're doing here, right? Except here where you're constantly using this SDS loss here to basically make sure that this frog always looks like the frog from the video, right? That's where you're using this SDS. Here they're pulling from the zebra, so they're kind of trying to make all the multi-views of this rocking horse look more like the zebra. So it's like slowly diffusing out the zebra. Architecture of the stable SSD nerf. So this is another triplane nerf. You see that? Yet another triplane nerf. Here's your triplane nerf here. And then here you go. Here's another triplane nerf. Here they've actually shown you. So these planes, you can basically see it as feature planes. So each of these planes has some little vector for each point in that plane that represents the feature at that specific point in space. So then if you want to know what the feature vector is for a random point in 3D space, you can then project that into each of those three planes and then get those three little vectors and then combine those, and then that's the feature vector or the representation for that specific voxel in 3D space. And it's how you can go from two-dimensional feature planes like this into a three-dimensional quote-unquote feature plane. This is a stable diffusion plus LoRa. So at the very beginning here, adapter, you see that? So the adapter is a LoRa, which is a low-rank adapter. A low-rank adapter is basically like an extra set of trainable weights, right? You're taking some subset of the original model. Here it's a stable diffusion, which is a UNet denoiser, right? And you're saying, okay, these specific parts of that stable diffusion model, I'm going to make these little LoRas, which are little extra weights. I'm going to push gradients into those LoRas. So you notice how most of this model is frozen. The only thing that they're changing is this LoRa. Once you have that LoRa, you can combine it with the original model or merge it in, right? You could think of it like it's a bunch of delta W's, and then you're just adding those delta W's to the original W's. But this stable diffusion, which has been fine-tuned, and the fine-tune is only in that LoRa, and you see here it's conditioned on this text, it's seemingly generating this latent here. So it's a latent diffusion model, and this latent is then being broken up into these three, probably sliced into these three planes here, and then a decoder turns that into the feature planes. And then once you have that, then you can condition a nerf on the features inside this triplane, and ultimately you get the nerf. So this is a nerf here. Comparison of mesh-based image to 3D methods in the wild images. So here they're comparing to 1, 2, 3, 4, 5 plus plus, which I think they compare to here as well. Here's 0, 1, 2, 3 XL, 0, 1, 2, 3. This is the problem with these papers, is like they're all comparing to a bunch of different things, and none of them are comparing to consistent things. VFU, LGM, Open LRM. Okay, so none of these. What does this one compare to? Com4D. No, this isn't even going to be the same. MV Edit, Dreamcraft, 1, 2, 3, 4, 5. This one seems good-ish. See, none of these have the Yanis problem. You see, we're already done with that. You remember, like, all those 3D papers that we were reading where they always had this Yanis problem where, like, you would have the face on the back of the head? None of these have the face on the back of the head, so that's already ancient history. These are pretty legit. I mean, I'd almost say this one's better. I don't know if this is state of the art. It seems pretty much on par with these things that they're comparing it to. And then here you have the text-guided texture generation. So you've already created the 3D representation, and I guess you're storing the mesh, but meshes have a texture that wraps on top of it, and I guess the text guiding will only change the texture. So here, I guess they're feeding this prompt, and then they're basically multi-view pushing gradients, multi-view pushing gradients, multi-view pushing gradients. And in that way, you can basically change the texture. So you see it's always the same mesh, but now you have different textures. Blip generated text prompts. Blip is another, it's kind of like a clip. May not accurately reflect, so it's possible to generate texture maps that align perfectly with the prompts. Okay. Let's see what our summaries have to say. I just hit 10K subs. Fuck yeah. Thanks, everybody. Makes me feel good. I think one of them does, if you go to the project page, it shows the models revolving. Oh, you're saying if I go to this thing, I can see the little 3D? Let's see. Look at that. Pretty good. Wow, it even gets the text on the back of this guy's shirt. That never mind, it doesn't. I was about to say, that's pretty crazy if it gets the text on this shirt, but it does not. It's just a bunch of garbage. I mean, it's pretty good, guys. This stuff is getting really good really fast. I mean, some of this topology is still cursed, but, you know, overall, this is pretty high level. Ooh, wait, look at that. That's no good. Look at this. So you see, oh, it looks fine. And then you zoom in. Look at that. There's crap in here. There's a bunch of worthless, like, floater crap inside. Oh, no. All right, whatever. We'll forget about that. All right. Let's see this. Let's read the little summary. Let's read Gemini 1.5 summary. MV-Edit introduces a training-free 3D adapter to extend pre-trained image diffusion models for 3D-aware diffusion. Pre-trained image diffusion models, 3D-aware diffusion. That seems fine. It's not a 3D adapter. It's just an adapter on a pre-trained diffusion model. Employs ancestral sampling to jointly denoise multi-view images and output high-quality textured meshes. That's not what it's outputting. It's outputting a nerf, and then the nerf can be used with marching cubes to output a mesh for efficient, high-quality 3D generation. Functions as a versatile 3D editor, enabling various tasks like text image to 3D, 3D to 3D, and high-quality texture synthesis. Achieves state-of-the-art performance in image to 3D and text to 3D guided. Okay. MV-Edit proposes a versatile 3D synthesis method using multi-view diffusion and a training-free 3D adapter, creating textured meshes from multi-view images in minutes, showing excellence in image to 3D and text-guided texture generation. MV-Edit functions as a 3D counterpart of SD-Edit, employing ancestral sampling to jointly denoise multi-view images and output high-quality textured meshes. Built on off-the-shelf diffusion models, MV-Edit achieves 3D consistency through the training-free 3D adapter. Pretty much all of these talk about this ancestral sampling, you know? I think they're probably in the same place that I am, where they're like, what the fuck is this? Let's look it up. Let's look it up. Control F, ancestral sampling. Ancestral sampling paradigm. Ancestral sampling paradigm. Ancestral sampling. Ancestral sampling. Performs ancestral sampling. Where is it? Explain this to me. Thus completing the ancestral sampling. Okay, so what is ancestral sampling? Recursive denoising until reaching the denoise state. Recursive denoising. So you're denoising recursively, so using your previous output as input to your thing again. So move forward to the next step. This less noisy image, we adopt the DDPM solver. Blah, blah, blah. User specified time step. Remove the denoised image from the predicted noise. Okay, so I I'm still not 100% sure, but it seems to me like ancestral sampling just means the ancestral refers to previous steps in the noise schedule or the noise step, right? These diffusion models are doing it over a series of time steps, and the ancestors are probably the previous time steps. That's what I'm guessing, but I don't know. Maybe one of you guys knows that. Can we try on our input images too? Have you guys seen T-Rex 2? Question by Atul. No, I haven't. What is T-Rex 2? All right, let's look at this one. Compress 3D. International Digital Economy Academy. What a great place to work. Compress 3D, a compressed latent space for 3D generation from a single image. Generated 3D models with and without texture. 3D generation with witness advantages. 3D assets from a single image. So this is going to be image to 3D. We present a triplane autoencoder. All right, there's that triplane. Everybody's loving these triplane latents. Look at that. From a colored point cloud. Here's your reconstruction loss. So they're probably going to train this autoencoder with a 3D data set. Which 3D data set are they going to use? Probably ComboVerse. Or did they just use OpenShape, this one? Utilize the clip model. How are you training this? Where are you getting this input and output? Decoder, triplane decoder. Here's another representation of a triplane. This one's nice because it shows you how you would project a point into each of the triplanes. Capable of generating a high-quality mesh, the sine distance function, and vertex deformation. We concatenate the triplane features of the 8 vertices of the cube and predict the cube weight using an MLP layer. So yet another nerf, it seems. Let's see. Encodes the 3D models into a triplane latent space. Within the autoencoder framework, we introduce a 3D-aware cross-attention mechanism which utilizes low-resolution latent representations to query features from a high-dimensional 3D feature volume. High-resolution 3D feature volume, which is your triplane latent space, thereby enhancing the representation capacity of the latent space. Subsequently, we train a diffusion model on this refined latent space. In contrast to solely relying on image embeddings for 3D generation, our proposed method advocates for the simultaneous utilization of both image embeddings and shape embeddings as conditions. So image embeddings is probably the color, and then the shape embedding, you see it's coming from this nerf where the output, you see this little multi-layer perceptron, it's probably not, so you can, the multi-layer perceptron, these nerfs, right, what it outputs, it can be different, right? So you can output, for example, the color and the radiance at a specific point in space, but another thing you can output is also this sine distance function, which is, you could think of it as kind of the distance to the surface of the object, right? And the sine distance function is, you can define that at any point within this voxel of 3D space that this MLP is implicitly representing. So they encode the image. So now you have the image embedding, which is kind of the semantic content of the image. Then they use the image embedding average pool. So reduce that dimensionality, use it to condition at the different layers of the nerf. So you can see here some skip connections in this nerf. I'm calling it a nerf because it says MLP, but it's not actually a nerf. This is a multi-layer perceptron that is trying to output a signed distance function. That signed distance function is ultimately going to produce this shape embedding. And that shape embedding is combined with the image embedding and is used to condition this triplane U-net. This triplane U-net is probably trained to be consistent with the representation that you get in this triplane autoencoder, which is then probably trained with a data set. But I don't know whether that data set is like an explicit 3D data set or whether it's a data set or whether they're using one of the other pre-trained 3D generative models to... here we go. To train this diffusion prior model, we first use the OpenShape model pre-trained on a large-scale 3D dataset. So this is ultimately where it's coming. So the OpenShape model is where your signal's coming from, and ultimately it's all kind of flowing in from that. Extract the shape embedding of the 3D model and the image embedding of the single view rendering image. This is no good, right? The problem with that is that this image embedding here, especially when you're using clip, right? It's just encoding pink frosting with cake, right? But because it's a single view, you're not getting all of the information, right? So like here, an important part of this image is the fact that this is a cupcake and it has a depth to it, right? But from this view, it just looks like a cake. So this image embedding here, this representation, probably doesn't account for the fact that this is a cupcake and it has a height to it, right? Because it doesn't know that. It's only seen a single image. So that's a problem with single view rendering being used to create the image embedding. Then we design an MLP with skip connections at different depths as the diffusion backbone to generate a shape embedding. It's a diffusion. This diffusion backbone consists of multiple MLP res blocks. Time step embedding is addition. What? Huh, so wait, so this little MLP is it's a little diffusion model. Look at that. It's a tiny little diffusion model. So normally an MLP, right, is just a multi-layer perceptron, and the layers are either the same width, or maybe they're wider at the bottom and then they get slightly less wide at the top. But you see here how it's wide and then narrow and then wide again, right? So it's the bottleneck shape, this VAE kind of like wide, then narrow in the middle. So this is actually a tiny little diffusion model where it's going from this, whatever this is, what is that? Some kind of like noise shape embedding, and it's going into the real shape embedding here. That's fucking crazy. Tiny little diffusion model to create the shape embedding, and then that shape embedding is combined with the image embedding to feed into this much larger diffusion model that uses a U-Net and diffuses out the triplane latents from Z of T, which is probably noise. That is pretty cool. We use each point feature on the triplane to query a corresponding cube region of the feature volume. In addition, we add a position embedding to the volume feature. Okay, so here they're talking about point feature on the triplane, right? I think this shows it the best here. But right, in these triplanes, right, if you want to know what the representation is at this point in space, you basically say, okay, well, what's the corresponding little area of the XZ triplane? Okay, that's going to be some 1 by 1 by 32, so it's going to be some 32-dimensional vector, right? Each triplane is a 128 by 128 image with 32 channels. So each little dot here is going to be one 32-dimensional vector, and then this dot here is going to be another 32-dimensional vector, and then this dot here is going to be another 32-dimensional vector, and then they concatenate them. So now you have 32 plus 32 plus 32, and that is going to be your little triplane representation. In this case, it's not a triplane anymore. Now it's just a feature vector, and you feed that into your color MLP. This is an actual nerf, right? So a multi-layer perceptron that consumes a feature vector for a specific point in space and then outputs a color. That is much more similar to a nerf, and then that's how you ultimately get that. Okay. Let me see the triplane auto data curation. There it is. I knew it. I was like, there's no fucking way this isn't using Objaverse, because they all use Objaverse. If you're starting from, if you have to train something like this that requires full 3D models, it's like the best one is Objaverse. So I was like, where the fuck is it? There it is. Filtered Objaverse dataset. There are many low-quality models. So in the original Objaverse dataset, that seems like a typo right there. That should be original. So they filter it. We manually annotated about 2,500 3D models. A good 3D model exhibits realistic textures and intricate geometric structures, whereas a bad 3D model is characterized by single color texture or simple shapes. I don't know about that. I think it needs to be correct. I think if you're intricate without needing to be intricate, it's a bad thing. You know, like, for example, some of these ones here, they're intricate without needing to be intricate, and that's a bad. Let's see if we can find a nice, yeah, like for example here, right? Like this is unnecessarily intricate here. Like you see all this weird like wobbly texture that they have on the head of the Mario. Like that's not a good thing. Like I would rather have this low poly if you're trying to do something like that. Same thing here, right? You see all this weird intricate texture that it created for these like muscles. That's not, I wouldn't say that's necessarily a good thing. I feel like this is a little bit better. So intricate doesn't necessarily mean bad or necessarily mean good. Sometimes it can be bad. Randomly select 5 random views and use a pre-trained clip. Concatenate these image embeddings, feed them into a shallow MLP. Despite the limited annotation data, we find that the trained MLP can correctly classify 3D models in most cases. That seems like a kind of bad benchmark for this classification. Here they're comparing to Shape E, which is OpenAI's. It's kind of old now, so, you know, not a great thing to compare against. This looks pretty clean, though. Look at this. Damn, look at these hands. Those are next level hands. You see, I've seen that? Holy shit. It's very clean hands. I mean, this blows it out of the water. This fish is so much better than these ones. These don't even look like anything. Oh, that's a great shot, too. So a lot of these 3D generative models, they're not trained on this kind of view. You see this view here? This is like the undershot of a fish. So it's like you're looking from underneath. The overwhelming majority of these use these kind of multi-view views, right? Where there's a bias here. There's an inductive bias that you're always kind of looking at the object from the top, kind of like almost like a 3/4 view from the top and then going all the way around. So usually you have biases like these, which means that the bottom of the objects is almost always trash because you're never really getting the multi-view of the bottom of the object. So this is a flex here when they're using this single image, which is the bottom of the fish, to condition it, right? So the fact that it can get this almost perfectly, this is very impressive compared to these other ones. You see how bad they are? It's because they've never really seen that bottom shot before. Pretty cool little paper. Let's see what our summaries have to say about that. So this is the Emergent Mind, which is a GPT-4 summary. So GPT-4 summary. Efficient method for generating high-quality 3D models from single images using a novel triplane autoencoder architecture. It is novel, but it's just a little bit, I don't know about novel. Triplane autoencoders are pretty popular, but I guess this is a slight different take on it, hence the word novel. Enhances generation fidelity by employing a dual conditioning strategy with image and shape embeddings. That's correct. You see it was conditioning this triplane unit with both image and shape embeddings. Experimental results show compressed 3D outperforms existing methods in speed, quality, and efficiency on standard benchmarks. I mean, all of these claim state-of-the-art, but at least this one actually does look pretty good based on that fish. Promises broader accessibility to advanced 3D modeling and opens new avenues for research. It's kind of a throwaway. All right, let's see what Gemini 1.5 has to say. Triplane autoencoder to compress 3D models into a compact latent space. Introduces 3D-aware cross-attention mechanism to enhance the representation capacity of the latent space, leading to more accurate and detailed 3D reconstructions. Achieves high-quality 3D generation from a single image with less training data and compared to existing methods in just 7 seconds on an A100. Let's see if that is correct. So we're going to spot check Gemini 1.5. Is this an A100? Control F, A100. Yeah, 7 seconds on a single A100, so it did get that correctly. You got to spot check your long context models because they make up shit all the time. Question from Akdan, can you scale a triplane? Yeah, you can choose whatever size you want. There's nothing that's preventing you from making this triplane bigger. So you see how each of the planes in this triplane is a 128 by 128 by 30. You could make this 256 by 256 by 7,742,000. You know, the only reason you wouldn't do that is because then you would try to push a gradient and it wouldn't fit on your GPU. But over time, you can expect these resolutions to get bigger and bigger and bigger and bigger, right? So the channel dimension will keep growing. There's plenty of scaling laws that show that the bigger you make this 32, the better, the more nuanced and intricate and correct the representation can be, right? The wider you make your neural nets is basically the same kind of concept where they can encode more things, but you're always trading off against compute and memory. So here they say high-res triplane 128 by 128 versus just a normal triplane, which is 32 by 32. So this is actually similar to what they're doing here. If you remember in this one, they denoise in this latent space, and then they go from a 40 by 40 by 12. So these are the triplane 40 by 40 by 12, and they turn it into an 80 by 80 by 48. Compared to here, this is a 128 by 128 by 30. Here they're putting the channel dimension last, but in this one they put the channel dimension first. So this one has 16 channels, and then each of the triplanes is an 80 by 80 square, and there's 3 of them. Here there's 3, each of them is 128 by 128, and then the channel dimension is 32. So this one is I kind of like this shape a little bit better. It's a more high res, and then this 32 is going to be more expressive than this 16. If I'm guessing correctly, given a triplane size, the 3D output will be in the same size as the triplane. No, so this triplane is ultimately used to condition a nerf, right? So ultimately, what you're going to be doing with that is you're going to be feeding that into a nerf model. Where is it? Let me see if I can find a pic for you. Yeah, you see this? Where what you're doing is you're feeding this each feature. So the nerf is defining a field, which means that a nerf is a neural network which is approximating a function, and that function is a field, which means that you can evaluate it at any point in space. So a nerf is infinite resolution in the fact that you can ask it what is the value at 0, 0, 0? And then you could say, what is the value at 0, 0, 0.000001, right? Which is basically a point that's just a tiny bit over there. And you can feed basically infinite resolution points into this nerf, and the nerf is going to give you something. Either it's going to give you a color, it's going to give you an opacity, it might give you a signed distance function, which is also a field, which means it's an infinite resolution. You can always query it at some other random point. And the triplane is just one of the things that goes into that. So if you say, hey, I want the color at this specific point in space, then you would say, okay, well, that specific point in space corresponds to these 3 pixels in these 3 triplanes, and I'm going to use those and feed those along with the normalized coordinates of the point in space that I want into this color MLP, and the nerf or the MLP output will produce some volume. So the final resolution of whatever you're doing here will depend on the marching cube hyperparameters that you have, and then just how many times you query this nerf here, right? If you query it 100 times, you're going to have 100 points, and then you can create the mesh from that. You could take this same nerve, query it 10 million times, and you would then feed those 10 million points into the marching cube and then get a higher resolution thing. What kind of PDF viewer do I use? I'm not even going to try saying your name. Is it Grzegorz? I don't know. It's like some kind of Polish name or something. But I'm using a a thing called PaperPile. I generally like it, but they don't pay me or anything, so I'm not gonna promote their product too much. It's great. There's a bunch of other PDF annotators. There's like a million of these at this point. Question from Cal. Are the number of layers in these architectures just the result of hyperparameter tuning, or are these just an arbitrary choice in the hidden layers? You can tune these. So there's plenty of these numbers that you could try different versions of them, right? So you could say, okay, well, what would it look like with 64 by 64 by 16? And then you could try what would it look like with 128 by 128 by 32, right? So there's some amount of hyperparameter tuning in that they're probably trying a couple different numbers. But in general, with these type of numbers, such as the resolution of the image or the dimension of the feature space, you already know the answer, right? The answer is going to be the higher resolution the image, the better the quality. The bigger the feature space, the better the quality. So some of these type of hyperparameters like this, you're not picking what you think is going to perform best because you kind of already know what's going to perform best. The biggest possible thing that you could pick is what's going to perform best. So usually what you're actually trying to pick when you're picking these is more the budget of the card that you want, right? So if you ultimately want to release this model such that people can use it on a GPU that only has 12 gigabytes of memory, you have to pick these numbers such that they're basically the maximum size that still allows it to fit on that GPU, right? But if you don't give a shit about that, right? So for example, OpenAI, when OpenAI trained Sora, right? And you know this from the way that Sam Altman described it in Lex Fridman interview, right? So one of the things that Sam Altman said about the Sora, he's like, we're going to try to release Sora, but right now the inference cost is too high. And he said, don't underestimate that. So what he meant when he said that is that Sora is the current state-of-the-art video generation model because they probably just 10x'd the previous size, right? Like Stable Video Diffusion, which is the video diffusion model they're using for this paper here, and this was trained by Stability AI, right? Stability AI wants you to be able to run this on your consumer GPU. They need to be able to train this with a limited budget, right, on the cloud. So they're not picking the most unreasonable size, right? But OpenAI, they don't give a shit about money. They don't give a shit about you running this locally on your computer. So they probably just used outrageously huge image resolution, outrageously huge feature size, outrageously deep network. So like probably every single number where they could have made it 10 times bigger, they did make it 10 times bigger. But the problem with that is that it takes an entire server rack to run Sora. So the inference cost is absolutely insane, and you're not going to have people just being able to generate video from that, because every single time you do inference, it's probably like hundreds of dollars. So hopefully that answers your question. Usually it's based on hardware constraints is like where ultimately these numbers come from. Yeah, number of channels is this. I call it the feature dimension sometimes, this 32, but yeah, it's also number of channels means the same thing because this is an image. Okay. That's that. Okay, now let's go to this one. LN3Diff. Scalable. I'm going to take off this hoodie. I'm done being hoodie man. I'm now no longer hoodie man. I'm also going to pour more yerba mate again. I'm also not sponsored by these guys, but if you don't have one of these like rapid heating kettles, you're totally missing out. I wonder if Grok's solution for inferencing hardware helps with the inferencing challenge. Grok is overhyped. So, here. Grok. So the problem with Grok nanometer. The Grok chips are based on 14 nanometer process. So the way that you understand how silicon works is that they're basically printing a pattern using lithography, which is kind of like you're projecting this pattern and then you're like creating this design, right? And there's only one company that makes the printers, and that's TSMC. TSMC, this one, right? TSMC is the Taiwanese company that makes these printers, right? So they make chips for everybody. You see, they make chips for Apple, they make chips for NVIDIA, they make chips for Qualcomm, and they don't worry about the design that's being printed on these chips. They only care about making the printers that create these chips, right? And over the years, they have better and better printers that can print smaller and smaller and smaller things, right? So nanometer of the 1080 GPU, right? So the GeForce GTX 1080 is a high-end graphics card made by NVIDIA that was made in 2016. It was built on the 16 nanometer process. If you look at the H100 chip, the H100 chip, which is made by NVIDIA, is made with the 4 nanometer process, right? And this was in 2023. So in 10 years, TSMC went from making a 16 nanometer printer to a printer that can do 4 nanometer. The Grok chip is 14 nanometers. Jesus Christ, why can't I just like find this? Nanometer. Somewhere on here. It might not be exactly 14. But ultimately, what Grok does is they said, hey, TSMC, do you remember that printer that you were using, that NVIDIA used to make their 1080s 10 years ago? You don't have anything running on that printer anymore because now NVIDIA is using your 4 nanometer printers. Can we use your 16 nanometer printer, but print our own design on it rather than NVIDIA's design? And TSMC is like, yeah, sure, we can do that. Here, you can use that printer. Nobody's really using it anyway, so feel free to use our 14 nanometer printer for your new Grok chip. Right? But what they get from that is they effectively get a 1080 that is optimized for speed, because whenever the GTX 1080 was designed by NVIDIA, it wasn't designed for graphics. It wasn't designed for deep learning. It was designed for gaming. So the 1080 is the actual thing that you printed, the design that NVIDIA made to print using TSMC's printers is intended for gaming. And it's only afterwards that people started using this for deep learning. So Grok doesn't actually have almost any memory. So this Grok chip here, let's see, Grok chip, can I like find a, blah, blah, is there like a stack? Hacker News? Can I get like a stats? Grok chip nanometer stats. Here we go. 230 megabytes of on-die memory. That's what I wanted to get at. That's nothing. So it's basically a 1080, blah, 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 14 nanometer. So it's made using the it's made using basically 10 years ago printer, and it has a very, very tiny amount of memory. So think about a GTX 3090, right? Which is 3090 nanometer. 3090 NVIDIA nanometer. This is the one that I have on this computer, right? So this is built using the 8 nanometer process, and it has something like 24 gigabytes of memory on it. The Grok chip has 230 megabytes on it, which is nothing, which means that even just to run a 70 gigabyte model, you need like 100 of these Grok chips in parallel. So Grok, the speed is very good, but it's because they sacrificed so many things for it. They sacrificed basically the memory. So if you had a Grok chip in your computer, you couldn't even load some of these models, right? And to our discussion that we were just having, this part here, the size of this determines the size of the model. So if you make this bigger, the memory needed on your chip to even load that model goes up. So you're not going to be able to load this model on a Grok chip just because it's such a tiny amount of memory. But then let me go back to kind of what I was meaning by this, is that TSMC is a big company. They service a bunch of these customers, and there's these relationships that they've built up over time, right? Apple and NVIDIA have been working with TSMC for decades. So whenever TSMC creates a new printer, they're not going to give it to Grok, right? Grok isn't going to have access to the new printer that NVIDIA and Apple get access to. They only get access to the sloppy second printer, the printer that NVIDIA stopped using 10 years ago. That's what Grok is using. So when I think about what the future of AI hardware looks like, it's going to be the companies that get the first access to the printers. So it's going to be NVIDIA and Apple because they have these relationships that they've built with TSMC. They're going to get exclusive access to the best printer. And then you're going to have this long tail of startups that get to make more specialized hardware designs on the older printers that are less resolution. So I don't know. I'm kind of like a NVIDIA takes all. I think NVIDIA and Apple kind of end up dominating this. Apple's not even in the race right now, but eventually they're going to be in the race, right? They're going to start making their own thing. But I just don't see how a startup can convince TSMC to let them use the good printers. So they're always going to be behind in terms of the generation of the printers that they're using. And because they're always going to be behind, they have this kind of narrative that like, hey, working at our designs that we're printing are so good that we beat the new ones. And it's like, no, it doesn't. You're not going to beat NVIDIA chips just by having slightly better designs. You're sacrificing something that the NVIDIA people already realized wasn't worth sacrificing. I don't know. That's my opinion on Grok chips. Yeah, Snooks is correct. It's not even, TSMC doesn't even make the printers. It's like a Dutch company called ASML. But they make the printer, and then TSMC makes the whole system surrounding the printer. But it's pretty weak, right? Because the entire supply chain is based on this like one very weak link in a particularly geopolitically kind of like contentious area that is Taiwan. So it's kind of sketchy. I don't know why we don't have our own version of this in the US, right? We should have this entire, like everything from raw material all the way to final working chip. Like that should be in the US, but you know, it takes a while to unwind kind of like the global supply chains that we've made. All right. Where were we at? We were here. I think we just reviewed that. We just reviewed this. We were looking at this one. That's right. All right. What do we got here? We got S-Lab, Wangshuan Institute of Computer Technology, Shanghai AI Laboratory, LN3D Scalable Latent Neural Field Diffusion for Speedy 3D generation. Okay, so I bet you this is going to be a diffusion in latent neural field space, which basically means MLP. So it's probably diffusion of it in a triplane nerf, if I had to guess. Let's see. The field of neural renderings has witnessed significant progress with advancements in generative models and differentiable rendering techniques. Though 2D diffusion has achieved success, a unified 3D diffusion pipeline remains unsettled. That's true. LN3 diff enables high-quality, fast, generic conditional 3D generation. Our approach harnesses a 3D-aware architecture and variational autoencoder to encode the input image into a structured, compact, and latent 3D space. Okay, so that sounds a lot like the 3D... Where is it? Sounds a lot like this. Let me see if I can pull it up. This here, right? So here's a VAE autoencoder that encodes, in this case, it's encoding 3D point clouds into this triplane latent here, but that's kind of what's happening here, right? That's what they're saying here. A 3D latent space, such as a triplane representation. The latent is decoded by a transformer-based decoder into a high-capacity 3D neural field. Through training high-capacity 3D neural field, that's your NERF. So it's going to be a high-capacity means that the NERF, the little multi-layer perceptron that you're using to learn this function that is a field, it's going to be big. So high-capacity just is another way to say big. Through training a diffusion model on this 3D-aware latent space, our method achieves state-of-the-art performance, yet another state-of-the-art. We should have like a little state-of-the-art counter, like right back here, where I can just like click, and it like increments. On ShapeNet for 3D generation, monocular 3D reconstruction. So monocular single image, you feed a single image, and it gives you the 3D object. And conditional 3D generation, this is more text, conditioning on text, or maybe conditioning on a single image as well. Surpasses existing 3D diffusion methods in terms of inference speed, requiring no per instance optimization. So here they're talking about how a lot of these previous type methods, you have to look at, you're kind of optimizing the NERF or the Gaussian splats from multiple views, right? So you're like going to one specific view and then using like an SDS loss there to push gradients into the representation. Then you're going to a different view and then using some kind of reconstruction or SDS to push gradients into the representation, whether the representation is a NERF or a Gaussian splat. So the per instance optimization refers to having to do that for every single 3D object that you generate. It's like this multi-step process where you're doing that at every single object. Ideally, you want to get to something that requires no per instance optimization. You just feed it the image and it generates the 3D thing. Apparently TSMC is building a fab in Arizona. That's a good idea. Our proposed LN3 diff represents a significant advancement in 3D generative modeling and holds promise for various applications in 3D vision and graphic tasks. Let's see, they have a little website. Let's check it out. High quality 3D mesh within 8 V100 seconds. I like this. This is great. Because a lot of times people are like in less than 1 second, and then they're using like a monster GPU. But here, this is letting you know that 8 seconds on a V100. So they realize that the time is meaningless unless you know what the hardware is. So here they say 8 seconds on a specific hardware, which is what you want to see. This one looks a little complicated. Let's see. Let's figure it out. Let's figure it out, guys. What exactly is going on here? Okay, in the 3D latent space learning stage, so as soon as they use that word stage, you know this is going to be a multi-stage process, and you can see here you have stage 1 and then you have stage 2. Okay, so this is like a 2-part process. So in this first part, a convolutional encoder, this is an encoder here. The convolutional refers to the fact that the architecture is a convnet, right? Could have been a transformer. Usually convnets aren't really popular right now, but you know, sometimes you got to do what you got to do. Encodes a monocular input image. Here's your single image. Monocular, just fancy way of saying a single input image. And then camera condition here is probably the extrinsic information. So basically the position of the camera. Maybe some intrinsic information there as well, such as the warping. The encoded 3D latent is further decoded by a 3D-aware DIT transformer DT. Here's your transformer. So it's consuming this 3-dimensional latent. Look at that 3-dimensional latent. You see 3 planes. That looks a lot like these triplanes. So they don't explicitly say triplane, but it looks a lot like a little triplane. guess, I don't know why they decode it again. So, okay, I guess this represents this. So this is the DIT. This is a diffusion transformer. This is the specific type of transformer that they're using here. Your transformer, you have your layer norms, you have your multi-headed attention, you have learnable position embeddings, you have your FFN, sometimes also called the feed-forward block or the multi-layer perceptron. Z is your 3D latent, so your 3D latent is being fed into a little multi-layer perceptron here, and then it's used to condition. You see here, it gets fed into the main path here of the transformer. Here you have your residual connections. Here you have also part of the layer norm getting fed in here after the feed-forward block as well. So this diffusion transformer is basically being conditioned on this latent representation, this what I assume is basically a triplane latent that is coming out of this convolutional encoder. There's n of these, so right, transformers have n blocks stacked on top of each other, reminiscent of how a feed-forward network or a multi-layer perceptron usually has multiple layers, so transformers all have multiple transformer blocks. Self-plane attention and then cross-plane attention. So this is kind of, you see this, for example, in the diffusion models for video, right? So in a lot of these video diffusion models, one popular thing that people do is they'll do attention mechanisms that are in the spatial and temporal dimension. So you'll have an attention mechanism where basically you're feeding in the spatial, which is like kind of the height and width, and then you have a temporal attention, which is looking at each frame over time, right? So it's basically a bunch of frames. The sequence of an attention mechanism is a mechanism that works with sequences. Here, in temporal attention, the sequence is frames over time. Here in spatial attention, the sequence is all the different parts of the image spatially. So this is a similar kind of thing. Self-plane attention means that within each individual plane, you're doing self-attention, so treating each plane almost as a kind of like an image in a spatial attention. And then cross-plane attention, this is kind of the equivalent of the temporal attention. So now you're looking at all the planes concatenated together, and then that sequence self-attention with itself. And that's how you get the cross-plane attention and the self-plane attention. So kind of a similar trick that we see in the video diffusion models over and over again, but here they're doing it for the 3 different orthogonal planes. That's kind of a cool little trick there. But they should have just done this entire thing together, right? Like, why have a conv encoder and a transformer, and like, I feel like you could probably figure out a way to make this encoder a diffusion. I guess you need this thing to condition it on, but I feel like you could combine this entire thing into just encoder decoder rather than encoder transformer upsampler. But okay. Because another way to view what's going on here is that basically this is just one giant encoder, right? Everything on this side is an encoder, and then this encoder has residual connections to this encoder via this 3D latent. All right. Upsampler, you get this, then you get your triplane, and then ultimately the gradients are coming in through here. Source view, random novel view, you have a geometry loss, you have a GAN loss, which means it's coming from some discriminator, and then you have a rendering loss. What are these losses? I think these are just different types of reconstruction loss. Further encoded 3D aware, which we perform self-plane attention, cross-plane attention. The transformer decoder latent, this is a typo, this should be decoder latent, is upsampled by a convolutional upsampler towards a high-res triplane. There's that triplane again for rendering supervisions. In the next stage, we perform conditional diffusion learning over the compact latent space. Okay, so now you have trained this encoder-decoder setup with this little transformer here. Then in stage 2, denoiser UNet, you're going to learn a diffusion model that produces latent planes. Okay, boom. This is exactly this fucking paper then. It's almost exactly the same. You're using, you're learning this encoder decoder where the bottleneck is these 3D triplanes, latents, and then you're learning a diffusion model that produces these latents. So it's like a latent diffusion model where you're removing the noise, starting from pure noise, and then removing noise until you get triplane latents, and then you're basically, you feed your whole data set into here and then use that to train this diffusion model. So same thing happening here. Just a couple differences and tricks, right? This one has the conditioning on the image embedding and the shape embedding. This one does not have that. This one is conditioning on a prompt or text. This one has this fancy self-plane versus cross-plane attention. This one, we don't really know what's in there. Let's see. "3D aware cross attention." Is this the same exact thing? "We employ 3D convolution in all three directions to convolve the normalized feature volume and obtain high-resolution triplane features. We propose a 3D aware cross attention which takes triplane features as queries. Computation, we first use blah, 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 blah. Leveraging low resolution." Yeah, okay, so this is actually doing a very, very similar thing. So it's a little bit more complicated because here they're doing this cross attention, but they're doing it with basically a convolution. So they're mashing some of the stuff together. You see how here they combine some of the kind of spatial receptive field with some of the temporal receptive field. I'm kind of overloading the terms spatial and temporal here, but it's kind of the same thing, right? You have attention that is within one of the triplanes and then attention between the triplanes, which is what I'm calling temporal, even though here it's not temporal in any way, right? Because it's just a single moment in time. But this is very, very similar to this. They're both just trying to give some way of attention mechanism looking at features on different triplanes and features within the triplane. So different ways of doing the same thing. Okay, I think I'm losing people. Let's see. What do we got? Sailboat with a mast. A blue plastic chair. Some of these look pretty good, but for each prompt we showcase 2 samples. These are ultimately nerfs. So these aren't meshes, these are nerfs. Which is why you get these fuzzy artifacts. It looks okay. It's definitely not state of the art. I don't know what the fuck they're talking about with state of the art. Yeah, I don't know. There's still plenty of mistakes in here. I'm looking at some of the quality on these chairs. A lot of the kind of like fuzzy artifacts, which means that the multi-view isn't consistent, right? The fuzz comes from the fact that from one view, you're seeing something and you're kind of generating the stuff in that view, but then when you look at it from the other view, the like axis is wrong, the depth is wrong, which is why you get that kind of like fuzzy look. And then ultimately that fuzzy look, whenever you actually try to turn it into a mesh with marching cubes, you're going to end up with these little floaters like that. ComboVerse. Okay. I think I know what this is. Let's look at the GPT summary. SLNFD introduces a scalable framework for high-quality, efficient, and versatile conditional 3D object generation. Seems fine. Variational autoencoder and a transformer-based decoder for efficient 3D-aware latent space encoding and data-efficient synthesis. I don't know if that's necessarily... I don't know. Employs latent diffusion learning and a unit architecture for denoising, significantly enhancing 3D reconstruction and generation quality. It's just like the like embellishing words here are just like a little bit triggering, like significantly enhancing. Versatile, efficient, like high quality. Like those words don't like mean anything, you know? I just feel like it should be a little bit more precise, but it's just reflecting what it read in the paper. So ultimately it's just going to do what it does. Demonstrates superior performance on ShapeNet benchmarks, showcasing advancements in 3D object generation and conditional synthesis. Kind of another throwaway sentence. Let's see what compressed 3D. Proposes triplane autoencoder to compress 3D models into a compact latent space. This isn't really about compressing 3D models. It's more about doing diffusion in this compressed latent space. Introduces a 3D-aware cross-attention mechanism to enhance the representation capacity of the latent space, leading to more accurate and detailed 3D reconstructions. I don't think it's enhancing the representation capacity. It's improving the representation capacity. The capacity is just a factor of the size, right? But the quality of the representation is going to depend on what things can pay attention to different things. So to me, the 3D-aware cross-attention is more about improving the quality of the representation rather than necessarily the pure capacity, which would just be like increasing the size of the channel dimension or something like that. Achieves high-quality 3D generation from a single image with less training data and time compared to existing methods. Generates 7 seconds on a high-quality GPU. Am I even reading the right thing here? No, I'm not. I'm reading this one. Holy shit, I'm already losing track. I'm not even reading the right thing, guys. Learning diffusion models over a compact 3D-aware latent space. That's much better. Utilizes 3D-aware architecture and VDAE to encode the input image into a structured and compact latent space. A transformer-based decoder then decodes the latent into a high-capacity 3D neural field. Okay. State-of-the-art performance on ShapeNet. Superior performance in monocular 3D reconstruction. Offers faster inference speed. Okay. That's fine. Damn, I was reading the summary for the wrong paper. What I want is this one, LN3Diff. Scalable framework for fast and high-quality conditional 3D generation, employing a 3D-aware architecture and VAE for encoding images into a latent space, significantly advancing 3D generative modeling in speed and quality. Yeah, I feel like they mostly get the right core idea here, which is this diffusion in the 3D triplane space. Generic conditional 3D generation. What does generic mean? That doesn't make any sense. Harnesses a 3D-aware architecture and a variational autoencoder. Diffusion model trained on this 3D-aware latent space achieves state-of-the-art performance on ShapeNet and surpasses existing 3D diffusion models. Okay. That seems fine. We're almost done, guys. We're on paper number 7 out of 9. So we've gone through 6 papers and we have 3 more to go. I think we're making good time. All right, we got another one from SLab. Is that the same group? Yeah, it is. SLab, Nanyang, SLab. Okay. Generating high-quality 3D assets from a given image is highly desirable in various applications. Recent advances explore feed-forward models that learn to infer the 3D model of an object without optimization. Though promising results have been achieved, these methods often struggle to model complex 3D assets that inherently contain multiple objects. Okay. ComboVerse. So seems like this paper is going to be about compositional, combining multiple 3D assets. 3D generation that produces high-quality 3D assets with complex compositions by learning to combine multiple models. I think these are... It's not models as in the actual neural networks. I think here they're talking about models as in 3D assets. We first perform an in-depth analysis of this multi-object gap from both model and data perspective. We seek to adjust their sizes, rotation angles, and locations to create a 3D asset that matches the given image. To automate this process, we apply spatially-aware score distillation sampling, so another take on the SDS loss, from pre-trained diffusion models to guide the positioning of the objects. Huh. So the size, rotation angle, and location, those are almost like the parameters of a Gaussian splat, right? So in Gaussian splatting, you're using gradients from these reconstruction losses in order to move the position and the rotation of these little Gaussian splats. But it seems like what they're doing in this paper is doing something similar, except what they're doing is they're combining objects. So you see how they have like, here they have a mesh representing this cat and then a mesh representing the lion. And it's almost like they're spatially positioning and rotating the object so that they're right on top. A blue toy box riding a lion. A skeleton wearing a helmet. So it's like combining multiple objects by pushing gradients directly into the position. Yeah, you see here? Learnable spatial relationship. So this is basically, learnable spatial relationship is, you could say that the Gaussian splats is effectively that, right? The Gaussian splats is a series of positions, rotations, like each little Gaussian splat has that. And here, each of these 3D objects has some vector that represents its relative position in world space. So this is like a Gaussian splat where each little Gaussian is a full 3D model. It's kind of cool. It's kind of cool. ComboVerse generates high-quality 3D models from a single image that contains multiple objects, a squirrel sitting on a paper box. We show textured meshes of created 3D content, showcasing stunning reconstruction quality. Pretty good, guys. Given an input image that contains multiple objects, our method can generate high-quality 3D assets through a two-stage process. Okay, so first stage is going to be single object reconstruction. In the single object, we decompose every single object in the image with object in painting and perform single image reconstruction to create individual 3D models. Decomposition and in painting. Okay, so they're going to have to segment out each object and then in paint the missing part. That seems fucking complicated. So you start with this image, you segment out the objects, probably with the segment anything model. Then you have the mask, you in-paint, so you use the mask to in-paint the missing part. You see how by taking out the fox, now you have all this missing part of the box. So you in-paint using Stable Diffusion with this mask in order to create the missing parts. Okay. Then once you do that, now you have two images of the two objects. Then you're going to use single image reconstruction to create each of these objects in 3D. Probably in the form of what? How do they reconstruct? Multi-object combination. I want single object reconstruction. Object in-painting, object composition. Ultimately, what is the format for the object? In-painted object can be reconstructed by image to 3D methods to produce a single 3D model. Okay, but what's in between these two? How are you making these 3D models? Combine the objects. Implementation details. They don't even tell you? Quantitative ablation. Where do they tell you what 3D... where is this reconstruction? What are you using for that? Input reconstruction. Input reconstruction. Okay. Leaking pattern. ComboVerse dataset features single object datasets. This is a good little reminder that ComboVerse is very object-centric, very single object-centric, so it basically has a very strong bias towards that. So if you have complicated objects, ComboVerse is going to be a bad prior, but there really isn't that many other priors to use, so you just have to deal with it. Okay, I don't think they're even going to tell us how they get the single image reconstruction. But then ultimately, that's step one. So now you have two 3D representations, whether it's a nerf, I think it's probably a nerf, but maybe it's a texture and a mesh. And once you have these 3D representations, it's probably a texture and a mesh if they have scale, rotation, translation. Then you have a 2D diffusion model, which is locked here. So that means it's frozen. That means it's probably Stable Diffusion. considering the prompt, a fox lying on a toolbox. All right, so you use this caption. This is the GPT symbol. So this caption, which is coming from the image, so they're feeding this image into GPT Vision. GPT Vision is producing this caption. This caption is being used to condition the attention maps of a frozen stable diffusion model. The frozen stable diffusion model generates some image. That image is used to push gradients into this composition here and ultimately push gradients into here. Okay. So it's basically very, very similar to a NERF or a Gaussian splat. In a Gaussian splat, you're rendering the splat from different views, which is what they're doing here. And then you're using something like a reconstruction loss, which you can kind of think of both of these as fancy versions of that. This SSDS, Spatially-Aware Score Distillation Sampling, I think they call it. That will allow you to push a gradient through the rendering, which is differentiable, right, in a Gaussian splat. And then here it's also differentiable. And you're pushing it all the way into these parameters. So over time, in this second part of the pipeline, what you're doing is you're basically updating the rotation vector, updating the scale vector, and updating the translation. So the fox is getting a little bit bigger, a little bit wider. It's rotating a little bit. And basically over time, it'll make it so that this fox sits right on top of that box. This is kind of cool. All right, so basically what this paper is ultimately trying to do, and just caveat, guys, like I have not read these papers, right? What I did before this stream is like yesterday I like read these abstracts and that's it, you know, and I fed them into GPT, but I have not read these papers. So it could be like maybe you read this paper and I'm about to tell you what I think it is and you're like, actually, he's wrong. I've read the full paper. That's totally fine. And if that's the case, go on Discord, let me know what I got wrong. But this is my guess, right? You guys have seen me. All I've done is just look at this figure. I read the abstract and I'm just going to make a guess here about what I think this is. But it seems to me what this paper is doing is it's basically making up for the fact that Objaverse has a very single object bias, right? Objaverse is only really a data set of 3D objects where there's a single object. So if you have a prompt that is complicated because it involves multiple pieces here, such as a toolbox and a fox, trying to generate a fox lying on a toolbox with one of these like kind of one-shot type techniques, like this one here, it's going to be difficult to do that. But maybe not these ones. I think these video diffusion ones are probably going to be able to get it. But if you're trying to do it with one of these type of models, these ones here, right, that have been trained with Objaverse, this encoder, this decoder, and ultimately this triplane latent representation space has the same object-centric and single object bias that you get from Objaverse, right? That's been like kind of passed forward because you've been training on it. So here they're saying, okay, well, what if we created each of those separately? So we create a fox, we create a toolbox, right? And the way that we do that is a little bit convoluted. We're segmenting out each part, doing in-painting, and then feeding each of the individual images into one of these reconstruction models. So now we have the two objects, and now we just need to figure out how to put them relative to each other, right? And in order to do that, we're effectively going to be doing almost like the same technique as a Gaussian splat, except rather than moving around millions or thousands of these little Gaussian splats, we're going to be moving around the relative position of these two objects. I think it's clever. I think it's like a nice little technique. It's definitely over-engineered though, because I think that you're not going to be doing this, that you're not going to have a multi-step pipeline involving in-painting and captioning and then single image reconstruction and then pushing gradients. Like, this is way too complicated. I think ultimately you're just going to be able to zero shot it from something like a video, right? I think these video diffusion models won't have the same object-centric bias, which means that you'll be able to generate compositional objects such as this guy riding this little boat, right? So as clever as this is, I think that it's just an over-engineered solution that works to patch up the limitations of our current level of scale and our current data sets such as Objaverse, but we're going to have better data sets than Objaverse that are created from these video diffusion models that are created from YouTube, right? So ultimately, once we stop using Objaverse, we won't have to deal with these biases that it introduces, and we won't have to deal or create these over-engineered solutions to deal with those biases. It's like the draw the rest of the fucking owl meme. Kinda, but here you're using Stable Diffusion to draw the rest of the owl. You're using this mask, and then you're saying, okay, generate the rest of this box, which is why the top of it looks a little weird. You see, because here's the problem, is that this fox sitting on the box, you see how the shadow of the fox is on the box? So when you segment out the fox, the shadow is still there. So whenever you're using Stable Diffusion to in-paint the missing part of this box, Stable Diffusion is like, wait a second, there's shadows here, therefore there must be something on this box creating the shadows, therefore here you go, when I in-paint it, there's a bunch of weird random shit on top of this box to create the same shadows that the fox was creating. But you don't actually want the random shit on the box, right? Because ultimately you're going to put this fox on top of the box, which is why you're going to end up with this kind of fox sitting on top of the box, but the fox is kind of overlapping with a bunch of other weird shit that Stable Diffusion created on top of the box to give you the same shadows. So I say, it's the problem with these over-engineered solutions. It's like you engineer a way to fix a certain problem, and then in the engineering of the way to fix that problem, you introduce some other random problem, such as now the fact that you've introduced the shadow artifact things. All right, let's look at the summary. ComboVerse, very good name though. Huge plus for that name. ComboVerse introduces a novel framework to improve 3D asset creation from 2D images, focusing on multi-object scenes. It addresses the multi-object gap in generative models through a compositional approach and a spatially-aware score distillation sampling. SSDS enhances spatial congruity by reweighing the attention maps. Congruity. Is that GPT? Let's search. Did it just decide to put that in there, or is that in here? No, that's not in the original paragraph. Look at little GPT, little GPT-4 getting fancy on us, getting literally using fancy words. Spatial congruity. Proving superior in experiments for realistic and coherent 3D object placement. Empirical evaluations show ComboVerse significantly outperforms existing models in generating accurately positioning objects in complex 3D scenes. Okay. I mean, significantly outperforms, like there really isn't any other techniques to do that. You're state of the art automatically if nobody else is doing what you're doing, I suppose. Compress 3D. Proposes a triplane autoencoder to compress 3D models into compact. No, that's not the one we want. We want Combo. Did it not even summarize Combo? It did not. Huh. That's weird. There is no summary for the Combo paper in Gemini 1.5. We did totally give it, though. Here it is. Chen et al. 2024 ComboVerse. Let's see if it did know. Provide a summary of the ComboVerse paper. Gemini 1.5 takes a very long time because it has to go through this 150,000 tokens that I gave it in those PDFs. So it almost takes like 30 seconds. Let's read these summaries. ComboVerse introduces a framework for generating complex 3D assets by learning to spatially align multiple models. That seems correct. Employing spatially aware score distillation. That seems fine. Guiding object positioning, achieving superior results. Okay, that seems fine. Work presents a 3D generation framework, produces high-quality 3D assets with complex compositions by learning to combine multiple models. That seems fine. Framework automates the process of adjusting sizes, rotation angles, and locations of the reconstructed 3D models to match a given image using spatially aware score distillation sampling from pre-trained diffusion models. That also seems fine. I kind of like this summary a little bit better. It's a little bit more specific. All right. Summary of ComboVerse. Single object reconstruction. So much like we were unable to figure out what reconstruction model they use, the single image reconstruction, they don't even mention it. They just go directly from, reconstructed by image to 3D methods to produce a single 3D model. All right, now that we have these 3D models, we combine them, so we weren't able to figure out which one they use, and it looks like Gemini wasn't able either. It just says, using some kind of image to 3D method. Probably just this one, to be honest. Like, if it's this coming from the same lab, right? If this is the same S Lab, Shanghai Artificial Intelligence Laboratory, and you have other guys here, S Lab, Shanghai it's the same people, so they probably just used one of their 3D reconstruction models, but I don't know why they wouldn't mention it, right? Because if you mention it, that's a free citation, so why would they not cite it? Unless they may be using somebody else's 3D reconstruction model, which is why they don't mention it, so they don't have to cite it, and then that way they have one less citation for your competitors. Nefarious. Question from Cal. Do you know how these researchers go about making these new state-of-the-art arches? I don't mean to knock these guys because they seem to be some common line thinking, but most of these arcs feel more like a hodgepodge of fundamentals, along with some borrowed ideas from other teams. Curious what you think. Yeah, I mean, it's extremely difficult, if not impossible, to create an architecture that's truly novel from scratch and get state-of-the-art. Even something like a transformer or any of these papers, like, you're building on previous ideas. So novel doesn't need to mean that you made the entire thing from scratch, because that's, like I said, basically impossible. Usually you're just taking a bunch of little bits and pieces from other papers and then combining them. And in computer vision, because there's a tendency to kind of over-engineer, you almost have novelty for free, right? Because this is such a weird pipeline that's a combination of so many different pieces that, of course, it's going to be novel because nobody else has even tried to do this, right? So a lot of times you can get novel and state-of-the-art because you're combining the little chunks and pieces of the previous state-of-the-art in a novel way, and then now that you've combined all these little chunks and pieces, you kind of, there's more like total capacity, if you want. That's kind of like a very broad kind of statement there, but if you think about it, if you combine stable video diffusion with a nerf and with this other 3D reconstruction, and you're combining it with, it's like you're kind of taking the power of a bunch of different infinity stones, and all the infinity stones together are going to give you better performance than a single infinity stone. So this is a pattern that you see time and time again in these computer vision papers, where it's like you can get state-of-the-art and novel at the same time because you're kind of just the first person to even try doing this. But normally, state-of-the-art is very difficult to achieve, especially state-of-the-art for something generic like MNIST or something like that, because it's like people have already tried a bunch of different techniques, and you can't like combine. I don't know what I'm saying, but hopefully that answers some of your questions. Or not. I'm sorry I failed you. All right, let's get to this last one here. Or actually, there's two more. DreamReward. Text to 3D generation with human preference. Look at this pour. It's out of control. All right. Tsinghua, Shengshu, Beijing, China. So we got another Chinese paper here. 3D content from text prompts has shown remarkable progress. Current 3D methods often generate 3D results that do not align well with human preferences. In this paper, we present a comprehensive framework coined DreamReward to learn and improve 3D models from human preference feedback. Ooh, okay, so this is like a instruction tuning, but in 3D space. That's kind of cool. We collect 25K expert comparisons, RIP to the people who had to make these 25,000 comparisons, based on systematic annotation pipeline, including rating and ranking. Then we build Reward 3D, the first general purpose text to 3D human preference reward model to effectively encode human preferences. Building upon the 3D reward model, we finally perform theoretical analysis and present the Reward 3D learning feedback learning, a direct tuning algorithm to optimize multi-view diffusion models with a redefined scorer. Grounded by theoretical proof and extensive experiments, our DreamReward successfully generates high-fidelity and 3D consistent results with significant boosts in prompt alignment with human intention. Our results demonstrate the great potential for learning from human feedback to improve text-to-3D models. Okay. Prompt set. Vintage wooden car race, polished mahogany finish, classic design with spoked wheels. Reward 3D annotation. Okay, so you're sampling prompts from some set of prompts. You're using those prompts to generate multi-view images with some kind of diffusion model. Then you're getting humans to annotate these scores. So you have score, alignment, fidelity, consistency, right? So you could think of this as a supervised learning task. It's a supervised learning task where this is your input, these images, right? So there's 4 images, so you have 4 image encoders here, encoding each of the 4 images. Then what you want is you want this model, these encoders, to output the score, right? So the score output the alignment, which is whatever 0 to, what is this, 6, 0 to 6, 0 to 6, 0 to 6. And ultimately, you're doing a supervised loss here where you're basically saying, okay, whatever the, I should be able to feed these images in and get the scores, and those scores should match what the humans are giving me, right? And in order to do this type of supervised learning, you have to do annotations, right? So you're going back to old school deep learning where you have input and then human annotated output, and you have enough of those here, 25,000, which is, it's all right. You know, it's not it's not like 100,000, but it's definitely bigger than 10,000 or 1,000. So I would say it's a reasonable size for an instruction tuning data set. Let me blow my nose real quick. You're training this reward model. Okay, this is a little standard reward. XJ, CJ, XI, CI. I bet you this R theta is this entire model here. It's a reward model parameterized by theta. And then once you have this reward model, it can take a bunch of images and then give you the reward. And the reward is supposed to be like, this is a shit image. This is a good image. This image has high alignment. This image is low fidelity. And they're going to use this reward model to fine-tune a multi-view diffusion model. So you can see here, they take, where does this start? It starts from here. So you have a prompt. Ooh, misspelling the word prompt. They called it prop-mt. So you start with this prompt, and you start with what is this camera? Just an image, I guess. You're generating the image. Then you have this frozen multi-view diffusion model. You have the frozen reward model. The prompt is fed into the diffusion model. The diffusion model eventually creates these 4 multi-view images. The 4 multi-view images can be simultaneously fed into this reward model, which is producing this reward. That reward is somehow fed into this nerve. Okay, so I think I see what's happening. You're basically using the SDS loss to get the look good. It should look good, right? The nerf rendered at different views should kind of match the multiple views that you have here, right? So that's where the SDS loss is going to come in. But you're also going to be adding this additional loss, which is going to come from the reward model. So depending on how they do this, it's very similar to the instruction tuning that you see in language models. Instruction tuning in language models is done in 2 stages. So you have your pre-training, and then you have your instruction tuning. So in your instruction tuning, some of the newer methods, such as DPO, just go directly from this data set. Your instruction tuning directly from this annotated data set here, this reward data set. But some of the older ones, Some of the older instruction tuning methods first kind of distill this reward data set into a reward model, and then that reward model is used to then feed the gradients that encourage high score, high alignment, high fidelity, right? Which is supposed to encode the semantic subjective preferences of humans. But it seems like here they're doing it at the same time, so they don't have like a separate nerf multi-view diffusion stage and then a separate instruction reward tuning kind of stage. It seems like they're kind of like combining it all into just one process and then just running it. The problem with that is that you now have to choose some kind of weight. So you're going to have to weigh which one you want more, right? You're going to have a hyperparameter which determines the strength of the reward loss compared to this SDS loss coming from the multi-view diffusion. And those type of hyperparameters are very difficult to tune. But complexity of selected prompt, we conduct a filtering process with a selection of 250 prompts. Let's see. 3D model ranked. R represents the reward 3D model. Okay. What about this training detail? We use image reward as the backbone, combine them with cross-attention, and use an MLP to generate a scalar for preference comparison. During the training stage, we observe rapid convergence and consequent overfitting, which harms its performance. We freeze some backbone transformer layers, finding that proper number of fixed layers can improve the model's performance. We train reward 3D on a single 4090 GPU with a batch size set to 8. So it's not a very big GPU, which is why the batch size is small. And this is kind of weird, right? So you would think that Tsinghua University has something better than a 4090, but I guess that's what they're training on. Here's a little summary about SDS. Why do SDS generated 3D assets lack alignment? Diverges. Okay, the conditional distribution obtained by pre-trained diffusion models diverges from human preference and actual user prompt distributions. So ultimately, a diffusion model is generating samples from a true image distribution from noise, right? But it's not just image distribution, it's a conditional image distribution where ultimately you're generating images, XT, from some condition Y, which is usually text or encoded text. And they're saying here that that conditional distribution is different from the human preference image distribution. So like the images and user prompt distribution, so whenever people actually type things in, they want a specific aesthetic quality to the things that they generate. And that is different from the distribution that you're training these diffusion models on, which have no kind of aesthetic quality. It's just kind of generic 3D images from the internet, right? Including shit images. Consequently, 3D assets distilled from this deviant distribution, that's kind of weird use of the word deviant, but I like it, offer align with human preference to an even more pronounced degrees. Okay, so they're basically saying these diffusion models have the problem that they're just trying to match the distribution that of images that they were trained on, but that distribution of images that they were trained on is not aligned with the distribution of human preference and user prompt. So, okay, that makes sense. Due to the multi-step nature, fine-tuning a diffusion model is challenging in timestamp, where fine-tuning a diffusion model for generation typically requires fine-tuning the last 20 to 30%. Text-to-image tasks often only require the last 10 steps. 3D generation often requires over 1,000 steps, meaning over 20 times the computational workload. We have learned that the distribution followed by our current deviates significantly from the ideal distribution. Okay, so here you see PTR XTY. This is now the conditional distribution, but the little r there. So you see how this PTR XT given y is different from this PT XTY. That little r denotes that it's the reference, or not reference, reward. So it's like the ideal distribution, the one that you want that is human preferences. Okay, so now they have their SDS loss up here. Here's the reward loss. And then they're going to combine these with this. Here you go. This is the little hyperparameter that I was talking about, this lambda r here. So you have to decide how much do you care about this SDS versus how much do you care about this reward. You see? So if this lambda r is very small, what you're telling your model as you're pushing gradients is that I really, really want you to make the SDS loss better or lower. So focus on that. But if this lambda r is big, what you're telling it is I don't really give a shit about this SDS loss. I want you to really, really focus on this reward loss. And that this hyperparameter is usually a pain to tune. So, okay. I kind of see what's going on here. Statue, what the fuck is that? Artifacts? A delicate porcelain teacup painted with intricate flowers rests on a saucer. This looks pretty good. These are images from nerfs. I can kind of tell just from the fuzziness. Octopus whose arms are gently waving pencils. That's a great prompt. It doesn't quite get it, but that's a really cool prompt. User study in the rate. So this is the best way to determine the quality. A lot of people use these quantitative metrics. These are nicer. They have people look at these and then say which one they like the best, you know? So I kind of trust these a little bit more. It seems like DreamReward is better than these other ones, but the problem is that these other ones are shit, you know? They don't really compare to the ones that we've been looking at, which are the more up-to-date ones, and that's why everybody can claim state-of-the-art. Okay. Kind of makes sense. DreamReward. It's kind of like instruction tuning for 3D generation. Let's see what Gemini had to say about it. Focus on aligning text to 3D generation with human preferences by incorporating human feedback. I agree with that. It uses a human preference reward model. It's good. Effectively encodes human preferences. I don't know about effectively, but it's a start. Generates high-fidelity 3D consistent results with significant improvement in prompt alignment. Demonstrates the potential of learning from human feedback to improve text-to-3D models. Yeah, I think it's a good idea. You know, it's basically just introducing instruction tuning or preference tuning for generative 3D, which I think will be a part of generative 3D. Develops a framework to refine text-to-3D models based on human preference, utilizing a unique reward model and feedback learning algorithm. I mean, it's just supervised learning. That's what the reward model is. It's just supervised learning based on human annotated multi-view images. So I don't know. This is kind of a shit summary. This paper presents a comprehensive framework to learn and improve text-to-3D models from human preference feedback. Collect expert comparisons and build reward-free 3D, the first general-purpose text-to-3D human preference reward model. Okay, that's a better way to describe it. Present reward 3D feedback learning to optimize multi-view diffusion models, generating high-fidelity 3D consistent results with significant boosts in prompt alignment. Okay, I think I like this one a little bit better, but this is a little... Again, I just don't like significant boost. Like, this is just... What are we doing? Why are we using subjective, fuzzy adjectives? You know, just we need to use more precise language. All right. One more paper, guys. Cal, I get what you mean, but I still don't get what would qualify as worth trying. Maybe I'm overthinking it. Yeah, Cal, so maybe your question is more along the lines of like, how do you even get to that point, right? How do people even come up with this original idea? And part of the problem that you're alluding to is that like it seems like it's a lot of work to even try something, right? So like if it's a lot of work to try something, how do you even come up with how do you choose what to do if you don't know if it's going to work before you even do it, right? And I think that mostly just comes from intuition, right? So usually these slots here, these are the advisor slots. And the job of the advisor in kind of a academic research effort such as this is to come up with that idea, right? So usually these people here are the people actually writing the code, but the idea, sometimes it's the people here, but these people are supposed to validate that, right? So before you start a project like this, you meet and you talk with these more senior people and you basically figure out a point in idea space that is worth implementing. So you're like, hey, I've been doing this text to 3D generation, but one idea that I had was, how in language models we do instruction tuning and we basically are using these preference data sets in order to tune the language models to behavior that we prefer. What if we could do something similar with 3D stuff, right? So like there's some kernel of an idea there, and then these two guys, you sit down with them and they're going to kind of use their intuition that they've built over decades of being there, right? Because these are going to be the older guys. They've been here for decades. They've done probably hundreds of these computer vision papers. So they have some intuition about what's a good idea worth trying, what's not a good idea worth trying, what are the pitfalls of this idea, what are the pitfalls of that idea. So they'll kind of flesh it out and they'll be like, okay, yeah, that seems like a good idea. Here's a couple ways you could do it, right? And then these people go and actually start building out those things. But it's not, the original idea that you start with is usually not what you end up doing. Usually over the course of this project, you're going to run into a bunch of pitfalls. You're going to run into a bunch of situations where you're like, fuck, dude, this particular path that I was going down led nowhere. Now I need to go somewhere else. And then you're going to have to try a slightly different technique. And then ultimately the paper is not going to show that, right? These papers aren't comprehensive as much as we would like them to be. They're not showing you the entire process that they went to get to this final point. There's probably a couple dead ends that we just didn't see here, right? They're only presenting the one that finally ended up working. So I realize that from your point of view, it kind of looks like they just magically came up with this like idea, and you're like, how the fuck did they even know this was going to work? The answer is they didn't. They had some kernel of an idea, and then they refined that with their advisors, and then they went out and they explored down that path. They probably ran into a couple dead ends, and then the most promising final point that they got to, once the time kind of runs up, they write it all down into the paper, and then there you go. Maybe that was a little bit better of a response. I'm working on it, Cal. All right. We're at the last paper, guys. Where are we at? 10:51. Almost been 3 hours now. Let's see. GRM. Large Gaussian reconstruction model for efficient 3D reconstruction and generation. Stanford, Hong Kong, Shanghai AI Laboratory, Ant Group. We introduce GRM. Large-scale reconstructor capable of recovering 3D asset from sparse view images in around 0.1 seconds. But what is that reference to, right? We don't know what the fuck. Is this 0.1 seconds on an H100 or is that 0.1 seconds on a NVIDIA 1080? It's a big difference. GRM is a feed-forward transformer-based model that efficiently incorporates multi-view information to translate the input pixels into pixel-aligned Gaussians. All right, so we got another little Gaussian splat paper. Gaussian. So most of these papers have been nerfs, specifically triplane nerfs, but now we finally have a little 3D Gaussian. I think there was one or two other 3D Gaussian papers, but people still love their nerfs. Together, our transformer architecture and the use of 3D Gaussians unlock a scalable and efficient reconstruction framework. Extensive experimental results demonstrate the superiority of our method over alternatives regarding both reconstruction quality and efficiency. We also showcase the potential of GRM in generative tasks, text to 3D, by integrating it with the existing multi-view diffusion model. Okay, let's look at their results. They got a little Hugging Face demo. That's kind of cool. Can we plug something into this? Drop image. Generate. Okay, so first thing it did is it removed the background. Okay, go. It's taking forever, 20 seconds. Oh, you can choose different multi-view models. Oh, look at that. This is a little Gaussian splat here. And then I guess the mesh is broken, but you can turn a Gaussian splat into a mesh if you want. And then here's a little video. That's pretty good, pretty high quality. There's zero Janus problem on this. You see that? The back of the panda's head is perfect. Pretty cool. To save on VRAM, so what they're talking about here is that if you were to use a bigger GPU, it would cost them a lot more money, but they just want this demo to be free. So they're running this on like the cheapest Hugging Space instance. So that's why they're probably using very low settings, and it seems like they only have the 0, 1, 2, 3 plus plus, which everybody seems to use. Pretty cool. Pretty cool little thing. All right. Let's go to the actual figure. What do we got? Sparse view reconstruction. So sparse view reconstruction, sparse view and multi-view basically mean the same thing. Sparse view just means you have not a lot, but there's no like specific threshold there, right? It's not like 2 images is sparse and then 6 images is not sparse, right? So here it seems like 4 images, they're calling this sparse view, but you know, in some of these other papers, such as this one, right, 4 images is considered multi-view. So here they're calling this multi-view even though it's 4 images, and here they have 4 images and they call it sparse view. So making it sound a little bit better than it is, I guess. Rendering, here's your Gaussian splat. So this is just the centroid. So Gaussian splats, right, have little positions, rotations, they have some thickness to them. So this just shows you the center of each of those Gaussian splats so you can visualize the density of them. It's kind of a nice little visualization. And then here you have the mesh created from those. It's pretty good. Image to 3D, text to 3D. Oh, actually, this Spider-Man, I saw that one. Let's see. I remember seeing the Spider-Man. Finally, we'll be able to compare directly. Which one was it in? Was it in this one? Don't you guys remember seeing the Spider-Man? Where is he? Where is Spider-Man? Here? Here? Oh, it's a chase, dude. I gotta go through all these papers. Is it this one? Yes, it was this one. Here it is. Boom. We're going to be able to directly compare these. All right. Here's the Spider-Man. That compared to this. I don't know. Kind of looks... Let's see. Let's look at the quality of that mesh. This is a very terrible mesh, but it looks a little weird. Like there's a missing patch here in his armpit. Honestly, this like smooth mesh is like, I like this one the best. This is Wonder 3D 1, 2, 3, 4, 5 MV edit. So this one here. It's hard to tell, honestly. You know, the MV edit looks a little bit better. Huh. But it's completely different tech, right? MV edit, this is using a nerf. You see, this is nerfs are the underlying 3D representation. But this one here, this is a splat. So both of them, you can turn a Gaussian splat into a mesh and you can turn a nerf into a mesh. But I prefer Gaussian splats for a variety of other reasons. So 2 different 3D representations being used here. All right, let's actually look at what's going on. Given 4 input views, which can be generated from text or a single image. Okay, so if you have a text to multi-view model, you generate these 4 images, or you have an image to multi-view model, right? They don't really care. They say, just get these 4 images. However you get these 4 images is up to you, which I'm okay with, right? You could do it via these ones. So you could take what these guys did, which is fine-tune a video diffusion model to create these multi-view images. That's probably the best way to get these, right? These are older because 0, 1, 2, 3 plus and Instant 3D, these are based on distilling from Stable Diffusion, so generative image models, versus I think the future is using video models. So multi-view from video diffusion models will be the best way to get these, but whatever. Once you have these multi-view images, then we're going to tokenize them. Okay, so you're going to turn them into a bunch of little image patches, which is what you need to do in order to feed it into this vision transformer. This vision transformer is an encoder. Okay. And then upsampler, pixel shuffle versus windowed self-attention. Windowed self-attention, this means you're doing the self-attention, but you're constraining the receptive field of it, right? So it's not self-attention over the entire image sequence. It's like within specific windows, but let's see what those windows are. Our sparse view reconstructor estimates the underlying 3D scene in a single feed-forward pass using pixel-aligned Gaussians. The transformer-based sparse view reconstructor, equipped with a novel transformer-based upsampler, is capable of leveraging long-range visual cues to effectively generate a large number of 3D Gaussians. Okay, so the output of this upsampler, we can see that there's 4 tokenized images here representing the 4 images here. Here you end up with 4 vectors, I guess, each representing Gaussians, and then you somehow fuse these, right? Because you're going to have duplicates here for sure. All right, let's look at this upsampler. Let's see what they're doing. Is this it? Upsampler, GCM, transformer-based encoder. Okay, that seems fine. You're going from image space here, input image, H by W by 3, height by width by 3 channels, and there's actually going to be 4 of these concatenated together. Okay, so here's turning it into patches using a convolution. That's just cutting it up into these little patches, which is pretty common. What is this C? Where is the C coming from? C. Right here. Plucker, embedding. What the fuck is this C? Is that... Okay, I don't know what that's... I don't know where that C is coming from. Ah, camera poses. Okay, I should have guessed. Okay, so basically each image has a corresponding camera pose, right? That extrinsic camera information. And so the encoder here, which is parameterized by theta and this phi here, is consuming the images and the camera information for each image. Okay. Learnable position encodings. You love to see that. I think that's the superior types of position encodings as opposed to kind of more hard-coded ones. Transformer-based upsampler. All right, this is the novel part of this. We use a windowed attention to balance the need for non-local multi-view information and feasible computation costs. Okay, so what they're saying here is that you want the attention mechanism to be able to access all parts of this, right? So we keep seeing this time and time again, but just to kind of drive it home here, right? I think this one was the one that had it. Yeah. So in these triplane representations, your attention mechanisms, you're doing it in the spatial, so you have spatial self-attention, and then here you have attention between all the different planes. So ideally, if you had infinite compute, you would basically have a giant attention mechanism that was between every single image and every single image, and that would be global, right? Which means that any patch of any of these multiple views can pay attention to any other patch of any of the other views. But the problem with that is that that's just a huge ass attention map, right? Because it's attention squares quadratically with the size of the input sequence, and if your input sequence is every single one of your images, that's just way too much memory. So you have to figure out how to balance the need for global information with a feasible computation cost. And they're going to do this with windowed attention, which is attention that is limited to some specific window. So there's some limited spatial. So within the actual image, certain tokens can only pay attention to certain tokens within that window, but then also image to image, or what I call the temporal, there's also a window there. We construct multiple upsamplers, progressively upsample the features by factors of 2 until we reach the original input image resolution. So progressively upsample the features. What they're talking about here is actually, I think this picture shows it the best, right? This one here, right? Where you're starting with lower dimensional features here and you're upsampling them to higher dimensional. The dimensionality of the feature space stays the same here, but you have a higher resolution. So it's higher in the spatial, but the channel dimension is the same. I think here the channel dimension gets higher. We first quadruple the feature dimension. Okay, so it's going from whatever 32 to 64, and then more quadrupled, and doubles the spatial dimension. Okay, so very high capacity model. Upsampled feature maps are grouped and passed to self-attention with a sliding window of size W and Shift W. So this is the constraint in that receptive field. While the self-attention is performant within each distinct window, to maintain manageable memory, the overlap between shifted windows improves non-local information flow. Okay, so there's going to be overlap between these windows so that information can flow between those. This would actually, you know what they should do? They should do this with a Mamba. You know, I know that we're kind of biased towards Mambas. I feel like I'm kind of a Mamba fanboy, but this is exactly the type of shit that Mambas are good at, right? Very large sequences, very long sequences, and dealing with that. So rather than having this sliding window attention, feed this into a Mamba, see what happens. And there's another paper. So Cal, if you're looking at paper ideas, take this paper, replace this part right here with a Mamba, and there you go. That's a paper. It might not be state of the art, but it's at least novel, which is the only thing you need for a paper, right? Paper doesn't need to be state of the art. It just needs to be novel. After blocks, the context length expands to the same spatial dimension. We reshape the features back to 2D tensors, resulting in V feature maps with a resolution of H by W denoted as F. Okay. So ultimately, you're ending up with some feature maps, which are just features that encode each of these images, just semantic information for each of those images, and then that's what you're actually going to use for these Gaussians. How are you going to actually make Gaussians out of this? Rendering with Gaussian splatting. From the upsampled features, we predict the Gaussian attribute map. So the Gaussian attributes are the properties of each little individual Gaussian, right? Which means the position, the rotation, the color, the opacity, right? There's lots of different variants, but ultimately it's a bunch of little properties that are assigned to each little individual Gaussian. And there's a Gaussian splat is like a set of these Gaussians, hundreds of them, right? Separate linear heads, they're unprojected along the view ray according to the predicted depth from which a final image I and an alpha mask can be rendered. And then once you have this final image I, right, then because this entire pipeline is differentiable, you can then take this image, which you render from the Gaussian splat rendering, which is doing this like sorting and then rendering, and you use a reconstruction loss to this. So you're basically pushing a reconstruction loss between this and going all the way back through there and updating the parameters of the Gaussians to then update these feature maps to then update this crap here. Pretty good. Here are the different losses. So you have your standard kind of image reconstruction loss here. You have L2, perceptual loss, and then you have a masked loss. Just because they're the objects here, you have a very good idea of what's background, what's foreground, so you can add a masked component to that reconstruction loss. This is pretty good. All right, so basically, this is very similar to all the other papers, except it provides a very good counterpart where all of these other ones are using triplane nerfs, and this one is using Gaussian splats. So very, very interesting Let's see. SparseNet LGM. So here's the input, the multi-view, the sparse view, I guess they call it here, but it's just multiple views. Rs. I mean, this looks really fucking clean, guys. GT is ground truth because these are rendered objects, so they know the ground truth. Like, that's very good. This is just naive Gaussian splatting right here. LGM. MVLRM. Yeah, look at this, the little details there on the carriage. Pretty good. Let's see. Dude, what? Look at the quality on this shit, dude. This is advanced. Look at this peacock. Holy crap, the details on that peacock are next level. This is like... I just feel like Gaussian splats have a much higher representational capacity than nerfs. With a nerf, you're ultimately just smashing everything into this tiny little MLP, right? So ultimately, in a nerf, you're representing everything that's inside this voxel of space inside this little tiny MLP. And there's just not enough capacity in these little MLPs to deal with that. Versus a splat is so much more explicit, right? Because you have this set of Gaussian splats, and each little Gaussian splat has attributes, little properties, and you push gradients directly into that. But just the raw capacity of a Gaussian splat compared to like a nerf MLP is bigger. So I think that that's ultimately why you see this difference in quality. Right? It's not like the loss or any of this other crap. Like, they're all using the same data sets. They're all kind of distilling from the same data sets or stable diffusion or like what have you, right? So it's not like they're using more data or different data or there's something tricky going on. I think it's literally just coming down to like just Gaussian splats having a better, higher capacity than nerfs. Like, look at this. This is so much better. Like, this is trash. Got some cats. Got some pigs. Looking pretty good. Let's read the summary for this. Oh, this is the demo. GRM is a new approach to 3D reconstruction from sparse view images using pixel-aligned Gaussians for rapid and efficient process, leverages transformer-based architecture for converting pixels to 3D Gaussians, ensuring high-quality and consistent reconstructions. GRM achieves state-of-the-art performance in object-level 3D reconstruction and in generative tasks when combined with multi-view diffusion models. Future work could improve GRM by addressing its limitations and hallucinating unseen regions through probabilistic frameworks. Okay. GRM, large-scale reconstructor recovering a 3D asset from sparse view images, utilizes pure transformer architecture to translate input images into pixel-aligned Gaussians, which are then unprojected to create a dense set of 3D Gaussians. This design improves efficiency and quality, achieves state-of-the-art quality for speed for object-level sparse view 3D reconstruction, also enables fast and high-quality text-to-3D and image-to-3D generation. Okay. Large-scale model for rapid 3D reconstruction from sparse views, translating input into dense 3D Gaussians for efficient 3D representation, surpassing other methods in quality, showing potential generative applications. Introduces GRM, a large-scale reconstructor capable of recovering a 3D asset from sparse view images. GRM is feed-forward transformer model that efficiently incorporates multi-view information to translate input pixels into pixel-aligned Gaussians, which are unprojected to create a set of densely distributed 3D Gaussians representing a scene. The method demonstrates superiority. All right, that all seems fine. Blender scene constructed with our textured mesh. Dude, I mean, this is some of the best results I've seen. Like, look at this mask, like the back of the mask. That's crazy. All right. All right. Let's summarize these things. Or no, let's ask some high-level stuff. So let's go back to Gemini. Which of these papers use a NeRF representation and which ones use a Gaussian splat? Comment from the real thing. I hope the people behind Sora working on 3D, it seems to have an excellent object consistency. Yeah, you can bet that they're doing that. Imagine this paper, but with Sora. So this is a relatively simple situation here. You just have this reconstructor here, which you can train from scratch, and it is working in this native Gaussian splatting representation, which I think is the better of the two compared to NeRFs. So imagine this, but rather than using these like shitty text to 3D and image to 3D that are based on Stable Diffusion, using a multi-view diffusion video model that's based on Sora, right? Which I guess is kind of basically what they're doing here. But in this one, they're using this optical flow, which I think is kind of like not ideal. Like, but this plus this to get you this, and then you feed it into this, and then you train the largest possible version of this that you can. That's going to be absolutely crazy. And I bet you that's probably what they're doing at OpenAI. Because they do a lot of like point cloud type of stuff too, right? Like shape E, point E, like all of those. They love these explicit 3D representations. I feel like they don't do as much like NeRF type of stuff. So, or I think shape E might be a NeRF. I don't know. I'm starting to get confused. But that's what I would bet money on. NeRF versus Gaussian splats. NeRFs. Diffusion uses a NeRF. SV3D employs a NeRF. And MVEdit uses a NeRF. Compressed 3D uses a NeRF to generate a 3D model. DreamReward uses a NeRF for 3D representation. Gaussian splat. GaussianFlow focuses on improving 4D dynamic and 4D novel view synthesis and GRM. So that is correct. Those are the two splat papers, and then these other ones were the NeRF papers. While NeRF remains a popular choice for a 3D representation, Gaussian splats emerges as a promising alternative, particularly for its efficiency and ability to handle dynamic content. GRM leverages Gaussian splat to achieve state-of-the-art reconstruction quality. The choice of 3D representation depends on the specific goals and requirements of each method. NeRF may be preferred for its ability to represent fine detail, while Gaussian splat offers advantages in efficiency and scalability. So here what it's saying is that ultimately a NeRF is representing a field, which is a function that can be evaluated at any point in space. So technically a NeRF is infinite resolution in that you can just keep querying it at finer and finer resolutions. But the problem is that it's not like the representation is infinite. Like there's some coarseness to the representation that is being implicitly stored inside the NeRF MLP. So even though Gaussian splats are more explicit and there's like a limited set of them, so like past a certain point, you only have a limited set of splats, so you can only represent a certain amount of complexity in your scene. I feel like the splats are going to scale better than the NeRF. So having a million splats will be more than, at some point you're going to get to this like diminishing return where you have more than enough splats to get the level of quality and fine detail that you need, and then that should be enough. Did you guys hear Boo? She was yelling. Boo Boo? She's somewhere. All right. What are the data sets used in these papers? Let's see if it can find the data sets. It should tell us at least Objaverse, at least Stable Diffusion, right? Because a lot of these papers are using these generative models as data sets, basically. Damn, dude, that 30-second inference is absolutely brutal. All right. Internal data set of 100K 3D objects created by 3D modeling ops. Synthetic multi-view data set using a fine-tuned video diffusion model. This is EMU, so it didn't quite get that. It should have told us that it was the EMU. Objaverse, okay. Google scanned objects, Omni object. Consistent 4D data set. Real-world monocular videos. Planoptic video data set. Here's Objaverse again. ShapeNet. GSO. Filtered Objaverse. Labeled 3D. They didn't tell us that this was 25,000, so that's a little hit there. This is this one here. No, this one. Where they collect 25K annotated for human quality, so I feel like it should have told us that one. 110 prompts. Objaverse again. 200 text prompts. Objaverse emerges as the most commonly used dataset for training and evaluation across these papers. Other datasets like ShapeNet, FFQ, and GSO are also employed. Notably, DreamReward introduces a new labeled 3D dataset specifically designed for learning from human preferences. The choice of dataset depends on the specific goals and requirements of each method. Objaverse offers large and diverse. ShapeNet provides category-specific data suitable for evaluating single object generation. If you had to design, or if you had to predict what the model arc, what the 3D model, or what the generative 3D model of the future would look like, what do you think the 3D generative model of the future will look like? Let's do that. What do you think the generative 3D model of the future will look like? Be specific in your explanation. Let's give it that. It'll chew on that. Let's also ask GPT, and let's ask Claude. Let's see what we get. So GPT is already plopping out. Claude is plopping out. Let's see. Highly sophisticated. Okay, bunch of bogus adverts. Blah blah blah. Convergence of several. Okay, none of this means anything. Blah 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 blah. Outputs that are in. Okay, more garbage. More garbage. Efficient data. Okay, this is a bunch of garbage. See, it doesn't make the connection. Like, I feel like I as a human, I made the connection that, okay, you can use video diffusion models, which are ultimately coming from giant video data sets. That's probably the biggest source of signal that you can get. So when you think about future 3D generative models, like, it's going to be coming from videos like that. The signal is ultimately going to come from these giant video data sets. But this is just a bunch of nothing. Let's see if we get an answer here. Large scale data sets, techniques like compact latent spaces, efficient architectures, ensure 3D consistency. These are just not good. You see, this is what I'm saying. It's like, even though these big context models, this isn't necessarily big context, but like they're not good at like synthesis. It's like they're good at summarizing the text, but they're not like extrapolating well. You know, I feel like humans are still very good at you can look at something and you can look at something else and you can kind of extrapolate from both of those, but both GPT and Claude have a hard time doing that. They're just kind of listing all the different things that you found in these papers. Models capable of generating complex 3D assets. Techniques like Spatially-Aware. Model will incorporate human feedback. That's true. I think that'll be a part of it. Model will be able to reconstruct 3D assets from sparse view images quickly and accurately. I think this is true, where it'll be based on Gaussians, but the generative 3D model of the future will be a scalable, multi-view, consistent, cross-modal, and composition-aware model that utilizes latent space optimization and human preference alignment to generate high-quality 3D assets efficiently from various input modalities, including text, images, and sparse view observations. This is kind of nothing. Cross-modal doesn't even mean anything here. There's not any modalities. There's just images and text, I guess. All right. Semantic understanding. Deep semantic understanding. Interactive and intuitive user interfaces. Allowing users to describe voice commands, gestures, and augmented reality might also be integrating, making 3D modeling more interactive and engaging. I think this is definitely going to be true, right? The kind of like VR blender, you know, you can envision some software where you're sitting there with a VR headset and you're kind of like waving your hands and saying things and like you like go like this and the object spins and you're like, change the tail to this, and it like redoes the tail. So I can envision that kind of experience. Capable of learning from user, continuously improving. Yeah, so it mentions the preference feedback, which I think will definitely be a part of it. Multimodal data fusion. I think the videos is really the big part here. It doesn't want to... That's so much more important than images and text. Sensory data. Touch and sound. What? Okay. Save the best for last. Let's see what Gemini. Overall, the generative 3D model of the future will be a powerful and versatile tool capable of creating diverse and realistic 3D content. By combining the strengths of different approaches, incorporating human feedback, and develop, these models will revolutionize... Okay, this didn't say anything. On-device and real-time generation. I think that's important. Model efficiency and hardware acceleration. Future 3D generative models will be able to run on mobile devices. That's probably going to be true. Generative capabilities beyond static objects. I think the rigged skeletons for animation is probably going to disappear. I think it'll basically be four-dimensional Gaussians or just Gaussians that have some trajectory in space and move over time. Improved 3D representations. Yes, it'll definitely... I agree with this. We're going to move away from textures. We're going to move into either NeRFs or Gaussian splats or a combination. Deeper understanding. Limitations of current object-centric models. This is definitely true as well. All of these are based on ComboVerse, which is why they have this object-centric bias. Human feedback could be crucial. Involve techniques like RLHF. That's good because we didn't mention RLHF. It just it made the connection there that the reward model in the Dream whatever paper is basically RLHF. Multimodal conditioning, either text or images. Seems fine. Hybrid approach, both optimization-based and feed-forward methods. I think it'll be all feed-forward. I don't think you'll have these kind of like per-object optimization processes that just seems like over-engineered stuff that we have now. Hybrid approach could leverage. No, I think the problem is that ultimately you're going to want feed-forward because you're going to want some tiny model that you could run on a VR headset, right? So ultimately, it's going to have to be small and it's going to have to fit on a headset and it's going to have to be real-time, which means that you can't have a multi-step inference process. It's going to have to be like one shot in order to just get to the speed to where the user experience is good. But okay. LLMs are still a meme. At least they will replace the boring corporate drones that just speak in pre-programmed PC business language that circles back in circles. What? This stream was longer than the director's cut of Lord of the Rings trilogy. Good stuff. That's what we aspire to. All right. I think I'm going to summarize this. We're at 3.5 hours. I think we beat this to death. So let's summarize this stream and then give you back some time. All right. So today we reviewed 9 different papers in the field of generative 3D. This is creating 3D assets from texts and images. And this field is blowing up right now. There's a lot of progress, and we're getting very, very close to kind of the ultimate demo, which would be you sit there with a VR headset and you talk to the VR headset and it generates realities for you, right? That's the ultimate demo that all of these are working towards. None of these are necessarily there, right? These are still very slow. The quality's still not 100% there, but we're making progress. So we reviewed a bunch of papers. I'm going to try to summarize these papers extremely briefly. Diffusion 3D by Generative AI group at Meta. They basically take a video diffusion model, which generates videos. They fine-tune it on 3D data to get these multi-view video diffusion models. So a video diffusion model that produces this kind of like multiple view of an object, kind of like a 360 scan around an object. And then they use the multi-view data to push gradients into a NeRF with a triplane representation. And once you have a NeRF, you can use marching cubes to get a mesh. The next paper, we had Stable Diffusion, had their own version of this, Stability AI, RIP. Also doing something very, very similar, where they're basically pre-training or using a pre-trained video diffusion model, fine-tuning it to create a multi-view video diffusion model, and then using this multi-view video diffusion model to push gradients into a NeRF and then get a mesh using marching cubes. So basically the same exact thing, but with stable video diffusion as opposed to the EMU video, which is Meta's video diffusion model. And both of these, I think, are actually probably the best indication of what we're going to be doing in the future, which is likely going to be using Sora. Sora is going to be the state-of-the-art video diffusion model when they finally release it, probably in a couple of months. And here, they do use some of the videos from Sora, and they basically calculate the optical flow in those videos and use that optical flow to guide the optimization of a 4-dimensional Gaussian splat. Gaussian splat that you're used to is 3-dimensional, which is static, where each little Gaussian is basically sitting there in some point in space and has some color and some rotation. A 4D Gaussian splat means that you're now adding kind of basically the movement of those Gaussian splats over time. And here they're using optical flow as kind of like the signal to make sure that the Gaussian splats are both pixel aligned and also are consistent with the pixel space and also consistent with this flow. And they call this GaussianFlow. Next paper. This was generic 3D diffusion adapter using controlled multi-view editing. This one was a little bit more complicated. I honestly kind of forget what's going on here, but basically it's a NeRF and then a diffusion model. They're just combining NeRFs and diffusion models. Here's your triplane NeRF, and they're using text-guided texture generation. So basically, you feed some text into a diffusion model, it generates some image. That image is being used with some kind of reconstruction, SDS type loss to then make the image appear more like that thing. So you can see here they got rendered RGBD. This is like some overly complicated bullshit here, but ultimately you're taking the NeRF of something, making it look like more like the text. Okay. I think the adapter here comes from the fact that they use a LoRa. So they use a little LoRa combined with the Stable Diffusion. They're not actually pushing gradients into Stable Diffusion itself, just into this LoRa. Next paper. This was Compressed 3D, a compressed latent space for 3D generation in a single image. This one's kind of cool. So in this one, they're also using a they're training an autoencoder, And the bottleneck of the autoencoder is a triplane representation, which means that this is kind of like an already 3D representation, and you can use this triplane latent as the input for a nerf. So once you have this triplane latent, you can feed that into a nerf, and then you can use that nerf to get the object and then eventually get a mesh. But here what they're doing is they're actually doing diffusion in this triplane latent space. So similar to how most image diffusion models perform diffusion in the image space, this is instead going to be doing it in this 3D latent space, which is what you're using to then feed into the nerf. So kind of a cool little idea there of like leveraging the fact that this triplane latent space is more efficient so that you can do your diffusion there. They also have a little tiny diffusion model that determines the shape embedding, which is kind of like the shape information of this object. I'm blasting through these right now. Okay, LN3 diff. Which one was this? Yeah, okay, so this was a similar kind of idea where you're doing this latent diffusion. You're doing it in this compressed, here they're calling it 3D latent. It's the same triplane nerf, not a nerf, but it's a triplane representation of this 3D object. You're encoding into that. Then you have this transformer, which has spatial attention, so attention within each plane, and then it also has cross-plane attention, which you can kind of think of it like the temporal equivalent in a video diffusion model where you're looking at the different planes or the different frames. Once you learn this transformer encoder upsampler, then you can learn this latent diffusion model here, which is conditioned on this prompt and goes from noise into this latent triplane. And then once you have that latent triplane, you can use it for a little nerf. So this paper and this paper are actually very similar. Then we had this one. This one was a little weird one. So this is ComboVerse. So in ComboVerse, they combine a couple different things here. They basically take an image, they segment out the different parts of the image, they use 3D reconstruction models to generate 3D objects for each of the different parts of the image, and then very, very similar to a nerf, or to a Gaussian splat, they then use these reconstruction losses to push gradients into the position and rotation and translations of the objects such that they're compositionally better relative to each other. So the whole point is that rather than having kind of a squirrel that's floating over a box or something weird like that, it's like right on top of the box. Then we had this one, DreamReward. So in DreamReward, this is kind of like instruction tuning, but for 3D generation. They collect a giant data set of human preferences and scores for multi-view images. So they're feeding 4 different multi-view images. And then they have a bunch of human labelers sit there and say whether it's high quality or low quality. They use supervised learning to train a reward model. And then they combine that reward model combined with your standard SDS losses in order to push gradients into a nerf. And now you have a nerf representing the object. Then the last paper we looked at was GRM. And GRM, very similar to all the previous papers, right? You're using a multi-view to reconstruct a 3D object, except now rather than using nerfs and triplane nerfs as the underlying 3D representation, you're instead using Gaussian splats. And then Gaussian splats, much like nerfs, you can turn them into a mesh and a texture if you want to do that as well. And that's pretty much it, guys. You know, I don't think any of these are super high quality. I was most impressed by the Gaussian splat one. I thought this one had, I thought these were really nice. Like some of these are the nicest ones I've seen. All of them claim state of the art, but I don't know. It's very difficult to determine state of the art for these kind of things. I think we still got another year to go before we have, we kind of hit the top of the S curve. I think I've mentioned this before, but most technology is on this S curve where for when you're in the middle of the S curve, you make a lot of progress very quickly, and each generation is much better than the previous generation. But then eventually you get to this top of the S curve and it starts plateauing. I don't think we're near that plateau region. I think once you have Sora that gets released, and maybe you get the next version of Sora next year, I can envision some kind of Gaussian splat based thing that works off multi-view from Sora. And I think once we start having that, I think that will be the beginning of the top of the S-curve where we start having diminishing returns. So I don't know. Still got a couple years until we get to the point where we have indistinguishable 3D quality from images and text and audio. So get ready. Hope you guys found that interesting. I'm tired. Tomorrow, we're going to be looking at something much easier. So it's not going to be a monster stream. We're just going to be doing a shorter stream on Neuralink and Mind's Eye, some kind of like brain computer interface stuff. See what happens there. Maybe we end up using brain signals to generate 3D objects and not use text, right? Like how cool would that be if that demo that I was describing where you're sitting there in a VR headset, you're not talking to the VR headset, you're just thinking about what you want to see, and that signal is being used to condition a four-dimensional Gaussian that plays out in front of you. All right, the future we can all believe in. Thanks, 87, Ed, Leal, Cal, Real Thing, Joseph Enox, Oraz, Aries, Snooks, Mohammed, Chabaklid, Snools, Joseph, Gregor, Akdan, Atul, Majetti, Wool, Pasoglov. Who else? Long, Jay, Marco. Thanks everybody for listening. Hope you had a great time. See you guys tomorrow and see you guys later.